Welcome to Scientific Discovery Hub, your gateway to the wonders of the universe. Have you ever wondered what lies at the very edge of our solar system? Picture a frozen, invisible sphere swirling with icy relics, so distant that sunlight takes centuries to reach it. This is the Oort Cloud, a mysterious boundary between our sun's influence and the uncharted void of interstellar space. In this video, we'll embark on a mind-bending journey to uncover the secrets of this distant frontier and explore how it shapes our understanding of comets, planetary formation, and even the potential for life beyond Earth. From the Oort Cloud's role as a cosmic time capsule to the bizarre interstellar visitors like Oumuamua, we'll dive into the latest discoveries and theories that are redefining our place in the cosmos. You'll learn about the Kuiper Belt, a bustling neighborhood of icy bodies beyond Neptune, and how comets, born in these frigid realms, become dazzling time machines that reveal the solar system's violent past. We'll also investigate how passing stars and galactic tides stir up chaos in the Oort Cloud, sending comets hurtling toward the inner solar system and occasionally Earth. But that's not all. We'll explore cutting-edge topics like dark matter's subtle influence, the sun's protective heliosphere, and humanity's efforts to defend against cosmic threats. Along the way, we'll uncover how studying these distant regions helps us decode the origins of our solar system and glimpse the universal processes that shape planets across the galaxy. Whether you're a space enthusiast or new to astronomy, this video blends astrophysics, planetary science, and cosmic curiosity to take you where few have ventured. So buckle up for a journey beyond the Oort Cloud, where every icy fragment tells a story of creation, destruction, and the endless dance of celestial forces. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of the universe. Together, let's push the boundaries of knowledge and explore the infinite horizon. Ready to venture into the unknown? Let's begin. At the furthest reaches of the solar system, where the sun's light stretches into a faint whisper, lies a realm so distant that its very existence is inferred rather than seen. This is the Oort Cloud, a vast spherical shell of icy remnants, a cosmic graveyard of primordial material that has drifted undisturbed for billions of years. Imagine a hollow sphere encircling the sun, so immense that it would take a spacecraft millennia to traverse its boundaries. Here, the gravitational grip of the sun weakens to a mere suggestion, and the vacuum of space reigns in absolute silence. The Oort Cloud is not a place we can visit. It is a concept born from the gaps in our understanding, a testament to the limits of human exploration. Yet its significance transcends its invisibility. It is a key to unlocking the solar system's ancient past, a vault of icy relics that may hold answers to the origins of comets, the dynamics of planetary formation, and even the possibility of life beyond our own star. To contemplate the Oort Cloud is to grapple with the scale of the cosmos itself, a reminder that even in our own backyard, the universe conspires to remain enigmatic. This frozen expanse, though invisible to our telescopes, shapes the destiny of our solar system in profound ways. Long-period comets, those celestial wanderers with orbital periods stretching into thousands of years, are believed to originate from its depths. When the gravitational tides of the Milky Way or the passage of a nearby star perturb these distant objects, they begin their slow, spiraling descent toward the inner solar system. These icy visitors, glowing faintly in the cold dark, carry with them fragments of the primordial soup from which the planets were born. They are time capsules, untouched by the chaos of planetary evolution, offering a rare glimpse into the conditions that prevailed 4.6 billion years ago. Yet, for all their importance, the Oort Cloud remains a phantom in the night sky, a place defined not by what we see, but by what we cannot. Its existence is inferred from the trajectories of comets, a silent symphony of gravitational echoes that ripple across eons. In this way, the Oort Cloud is both a scientific puzzle and a poetic symbol of the unknown, a boundary where the sun's influence fades into the void and the universe begins anew. The Oort Cloud is a theoretical construct, a model devised to explain the observed behavior of long-period comets. Dutch astronomer Jan Oort first proposed its existence in 1950 after analyzing the orbits of comets that entered the inner solar system from seemingly random directions, unlike short-period comets which originate from the Kuiper Belt, a disk of icy bodies beyond Neptune. Long-period comets follow highly elliptical paths that suggest an origin far beyond the known planets. These comets' orbits often extend to tens of thousands of astronomical units, AU from the Sun, where 1 AU is the average distance between Earth and the Sun, approximately 150 million kilometers. At the outermost edge of the Oort Cloud, distances stretch to over 100,000 AU, a staggering 1.6 light-years, an expanse so vast that even at the speed of the Voyager spacecraft, it would take 300,000 years to reach. The Oort Cloud is thought to consist of two distinct regions, an outer, roughly spherical component, and an inner flattened disk-like structure. The outer cloud, influenced by the gravitational pull of the Milky Way and passing stars, is the source of most long-period comets. Its icy inhabitants, ranging from a few kilometers to hundreds of kilometers in diameter, are loosely bound to the Sun, their orbits easily disrupted by external forces. The inner cloud, sometimes called the Hills Cloud, after astronomer Jack G. Hills, is denser and less susceptible to perturbations. Together, these regions form a reservoir containing an estimated 100 billion to a trillion icy objects, each a relic from the solar system's infancy. These bodies, composed primarily of water ice, methane, ammonia, and carbon-based compounds, are remnants of the protoplanetary disk, from which the planets coalesced. Their surfaces, shielded from the Sun's heat and radiation, preserve the chemical signatures of the early solar nebula, offering scientists a unique window into the processes that shaped our cosmic neighborhood. Despite its hypothesized abundance, the Oort Cloud remains invisible to direct observation. The objects within it are too small, too dim, and too far away to reflect enough sunlight for even our most powerful telescopes to detect. Instead, its existence is confirmed through indirect evidence. The gravitational tugs that nudge comets from their distant perches and send them hurtling inward. For instance, when a star passes close to the solar system or the Sun traverses the dense spiral arms of the Milky Way, these gravitational influences can subtly alter the orbits of Oort Cloud objects. Over millions of years, these disturbances accumulate, occasionally dislodging a comet from its stable orbit and sending it on a chaotic journey toward the Sun. By tracking the trajectories of these comets, astronomers can extrapolate their points of origin, mapping the contours of the unseen cloud. This method, akin to inferring the shape of a hidden island by observing the ripples it creates in the ocean, underscores the ingenuity required to study a region that defies direct exploration. The Oort Cloud is more than just a repository of comets. It is a cosmic time capsule, a fossilized record of the solar system's earliest days. The icy bodies within it are thought to be pristine remnants from the protoplanetary disk, the swirling cloud of gas and dust that gave rise to the planets. Unlike the rocky planets and moons of the inner solar system, which have been reshaped by geological activity, collisions, and atmospheric erosion, the objects in the Oort Cloud have remained largely unchanged for billions of years. Their surfaces, frozen in time, may contain organic molecules, complex carbon-based compounds that could shed light on the origins of life. Some scientists speculate that comets from the Oort Cloud delivered water and organic materials to the early Earth, seeding the planet with the building blocks of biology. If true, then the very origins of life on our world may lie buried in the depths of this distant frigid shell. Yet, the Oort Cloud also challenges our understanding of planetary formation. Its sheer size and mass imply that the solar system once possessed significantly more material than it does today. Astronomers believe that gravitational interactions during the early stages of the solar system's evolution scattered many of these icy bodies outward, flinging them into the furthest reaches of the Sun's gravitational domain. This process, known as planetary migration, suggests that the architecture of the solar system was far more dynamic in its youth. The Oort Cloud in this context is a relic of that turbulent past, a graveyard of failed planets and discarded debris. But what else might it conceal? Could undiscovered worlds lurk within its depths? The possibility of a massive distant planet, often dubbed Planet 9 or Tyche, has been debated among scientists, though no conclusive evidence has been found. If such a body exists, it would further complicate our models of the solar system's formation and evolution, hinting at a complexity yet to be unraveled. Beyond its role in planetary science, the Oort Cloud raises profound questions about the nature of our place in the galaxy. If every star has a similar cloud, as theoretical models suggest, then the Milky Way may be filled with countless such reservoirs, each harboring its own population of comets. These icy wanderers, when disturbed by stellar encounters or galactic tides, might occasionally escape their native systems and drift through interstellar space. Some of these interstellar comets could even cross paths with other stars, potentially delivering their ancient cargo to new worlds. In this way, the Oort Cloud is not merely a boundary of our solar system. It is a bridge between stars, a silent participant in the grand exchange of cosmic material that spans the galaxy. However, the Oort Cloud also serves as a humbling reminder of how much remains unknown. Despite decades of research, we have never directly observed an object within it, and our knowledge of its properties is based on statistical modeling and indirect evidence. Future missions, such as the development of advanced infrared telescopes or interstellar probes capable of reaching the outer solar system, may one day provide the tools to peer into this hidden realm. Until then, the Oort Cloud remains a symbol of the vastness of the cosmos, a place where the sun's influence wanes and the universe itself seems to draw a breath before continuing its endless expansion, while the Oort Cloud marks the outermost edge of the sun's gravitational reach. Another region of icy wonders lies much closer to home. Between the orbit of Neptune and the distant Oort Cloud lies the Kuiper Belt, a densely populated disk of small icy bodies that serves as the birthplace of short-period comets. Unlike the Oort Cloud, the Kuiper Belt is a tangible frontier, partially explored by spacecraft such as NASA's New Horizons mission, which famously flew past Pluto in 2015 and later ventured into the uncharted depths of the trans-Neptunian region. This inner reservoir, though far less expansive than the Oort Cloud, is no less significant in unraveling the mysteries of the solar system. Its objects, including Pluto, Eris, and countless smaller worlds, offer insights into the processes that shape the outer planets and the distribution of primordial material. But the Kuiper Belt is not merely a relic of the past. It is a dynamic environment where gravitational interactions with Neptune and other giant planets sculpt the orbits of its inhabitants. Some of these objects, when nudged by Neptune's gravity, are sent on trajectories that bring them into the inner solar system, becoming the comets we observe today. Yet the Kuiper Belt may also hold clues to a more enigmatic phenomenon: the arrival of interstellar visitors like Oumuamua, the first known interstellar object to pass through our solar system. Discovered in 2017, Oumuamua's elongated shape and peculiar trajectory sparked speculation about its origins and composition. While it likely hails from another star system, its path through the Milky Way suggests that similar objects may frequently drift between stars, carried by the gravitational tides of galaxies. Could the Kuiper Belt serve as a launching point for such interstellar travelers? Or might some of its objects be captured remnants from neighboring systems, evidence of a cosmic exchange of material? As we turn our gaze from the Oort Cloud to the Kuiper Belt, we are reminded that the solar system is not an isolated entity, but a node in a vast network of celestial connections. The Kuiper Belt, with its icy bodies and dynamic interactions, invites us to explore the intricate dance of gravity and motion that binds the cosmos, and to ponder whether we are truly alone in the universe. In the quiet stillness of the night sky, where stars blink like ancient sentinels and planets drift in silent procession, the universe occasionally stirs with revelations that defy expectation. On October 19, 2017, the Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, in Hawaii captured an anomaly, a speck of light moving at a velocity incongruous with the familiar rhythms of our solar system. At first glance, it seemed unremarkable, another celestial body among countless others. Yet, as astronomers refined their observations, the truth emerged. This object, later named Oumuamua, a Hawaiian term meaning a messenger from afar arriving first, was not born within the cradle of our solar system. Instead, it had traveled billions of miles from the depths of interstellar space, a traveler unmoored from any known stellar home. Its arrival was both a scientific revolution and a poetic reminder of the boundless interconnectedness of the cosmos. Oumuamua's discovery shattered the long-held assumption that our solar system was an isolated pocket of order in the galactic sea. For centuries, humanity gazed outward, charting the orbits of planets and asteroids, believing that all such bodies originated from the same primordial cloud that gave rise to the sun and its retinue. Yet here was an interloper, a cosmic nomad whose trajectory bent sharply away from the sun, its path marked by a hyperbolic orbit, a telltale sign that it would never return. This was no ordinary comet or asteroid. It was a relic from another star system, a fragment of a world we had never seen, carried across the void by forces we barely comprehend. In its passing, Oumuamua invited a profound question. If one such object could reach us, how many more might be wandering unseen through the darkness, bearing secrets of distant stars and the chaotic dance of planetary formation? The story of Oumuamua is not merely a tale of scientific discovery. It is a meditation on the nature of existence itself. Every star in the night sky is a sun, each potentially surrounded by its own family of planets and the detritus of creation. In the grand tapestry of the Milky Way, collisions, gravitational tugs, and the violent births and deaths of worlds scatter fragments into the abyss. These interstellar wanderers, though fleeting in their appearances, are the echoes of ancient stellar nurseries, the whispers of galaxies colliding, and the remnants of cosmic upheavals. To study them is to glimpse the hidden architecture of the universe, to trace the invisible threads that bind together the scattered shards of matter drifting through the void. As we embark on this exploration of interstellar objects, we are not merely cataloging oddities in the night sky. We are stepping into the role of cosmic archaeologists, piecing together a narrative that stretches across star systems and spans eons. What do these wanderers reveal about the universality of planetary formation? Can they serve as ambassadors of life, carrying the seeds of biology from one world to another? And in the shadow of these questions, a more audacious thought lingers. Could these objects, or those yet to be found, bear messages from civilizations far beyond our own? The answers lie in the stars, and in the silent, enigmatic visitors who occasionally pass through our corner of the cosmos. To understand the significance of interstellar objects, we must first grasp the mechanics that govern their existence. Unlike the planets, moons, and asteroids that have spent billions of years orbiting the sun, these interlopers originate from the gravitational crucibles of other star systems. Their journeys begin in the tumultuous early stages of planetary formation, where young planets jostle for dominance, scattering debris in all directions. In these chaotic environments, gravitational interactions between massive planets and passing stars can hurl fragments of rock, ice, or metal into the interstellar void. These ejected remnants become the nomads of the galaxy, adrift in the cold, dark expanse until their paths intersect with other stars. The defining characteristic of interstellar objects is their hyperbolic orbit, a trajectory that diverges sharply from the closed loops of native solar system bodies. When an object approaches a star system, its path is shaped by the gravitational pull of that system. Most bodies within a solar system follow elliptical orbits, looping endlessly around their host star. However, an interstellar object arrives with a velocity greater than the escape velocity of the solar system, meaning it cannot be captured by the sun's gravity. Instead, it follows a hyperbolic path, a sharp, open curve that carries it back into the interstellar abyss. This distinction is crucial. It allows astronomers to identify interstellar visitors, even when they appear indistinguishable from native objects at first glance. The first confirmed interstellar object, Oumuamua, exhibited this hyperbolic orbit with startling clarity. Discovered by the Pan-STARRS telescope, it moved at a speed of approximately 87,000 kilometers per hour relative to the sun, far exceeding the velocities of objects bound to our solar system. Its trajectory suggested it had entered the solar system from the direction of the constellation Lyra, though the exact point of origin remains uncertain. What made Oumuamua particularly enigmatic was its peculiar shape. Observations revealed it to be elongated, resembling a cigar or a flat-sided disc, with a length-to-width ratio estimated at 6.7, an extreme deviation from the rounded forms typically observed in asteroids or comets. Furthermore, Oumuamua showed no signs of outgassing, the release of volatile gases that characterizes cometary activity. This absence of a coma or tail puzzled scientists, leading to debates about whether it was an asteroid, a comet stripped of its volatiles, or something entirely novel. The second confirmed interstellar visitor, Comet 2I Borisov, arrived in late 2019 and offered a contrasting perspective. Discovered by amateur astronomer Gennady Borisov, 2I Borisov displayed classic cometary behavior, emitting a glowing coma and a distinct tail as it approached the Sun. Spectroscopic analysis revealed the presence of carbon monoxide and water vapor, chemicals commonly found in comets within our own solar system. This similarity suggested that 2I Borisov originated in a star system with conditions analogous to our own, where icy bodies formed in the outer reaches and were subsequently ejected into interstellar space. Unlike Oumuamua, 2I Borisov followed a more predictable trajectory, its hyperbolic orbit clearly indicating its extraterrestrial origin. Together, these two objects provided a rare dual perspective on the diversity of interstellar bodies, hinting at the vast range of environments that may exist across the galaxy. The study of interstellar objects is not merely an exercise in taxonomy, it is a window into the processes that shape planetary systems. By analyzing the composition, size, and orbital dynamics of these wanderers, scientists can infer the conditions under which they were formed. For instance, the presence of volatile compounds like water and methane in 2I Borisov suggests that its parent system had a cold outer region where such materials could condense, a feature shared by many known exoplanetary systems. Conversely, Oumuamua's lack of volatiles and its unusual shape raise intriguing questions about its formation history. Was it sculpted by the intense radiation of a nearby star? Did it originate in a system where solid bodies coalesced under different physical laws? These uncertainties underscore the limitations of our current understanding and highlight the need for further observation of interstellar visitors. Moreover, the detection of these objects relies on cutting-edge technology and global collaboration. Facilities like Pan-STARRS, the Zwicky Transient Facility, and the upcoming Vera C. Rubin Observatory are designed to scan the skies for transient phenomena, including interstellar interlopers. These surveys operate on the principle that early detection is key to tracking and studying these fast-moving objects before they vanish into the depths of space. The algorithms used to sift through astronomical data are continually refined to distinguish interstellar candidates from native solar system bodies, a process that involves modeling their trajectories against the gravitational influences of the Sun, planets, and even the Milky Way itself. As our observational capabilities improve, so too does our ability to characterize interstellar objects in unprecedented detail. Future missions, such as the proposed Interstellar Probe, aim to intercept such bodies directly, providing close-up analyses of their surfaces and interiors. These endeavors promise to unlock the secrets of their origins, revealing whether they are mere debris from planetary chaos or something more extraordinary. In the meantime, every new interstellar visitor brings us closer to answering one of the most profound questions in astronomy. How common are planetary systems like our own, and what role do these cosmic wanderers play in shaping the evolution of the universe? The arrival of interstellar objects like Oumuamua and 2I Borisov compels us to reconsider the boundaries of our understanding. For millennia, humanity has pondered whether Earth is unique in harboring life, and whether our solar system is an anomaly in the cosmic scheme. These wanderers, however, suggest that the processes that birthed our own planets, collisions, accretion, and gravitational expulsion, are not exclusive to our corner of the galaxy. If such events are common, then interstellar objects are not rare curiosities, but a natural byproduct of planetary formation throughout the Milky Way. This realization reframes our perception of the universe, transforming it from a collection of isolated systems into a dynamic, interconnected web of exchange. One of the most tantalizing implications of interstellar objects is their potential role in the distribution of life. The theory of panspermia posits that life's building blocks, or even microbial organisms, could hitch rides on comets, asteroids, or interstellar debris, traveling between star systems to seed new worlds. While this hypothesis remains controversial, the discovery of organic molecules in both Oumuamua and Tuai Borisov lends credence to the idea that such materials are abundant in the cosmos. For instance, spectroscopic analysis of Tuai Borisov revealed the presence of carbon-based compounds, essential precursors to amino acids. If similar objects frequently traverse the galaxy, they could act as cosmic couriers, ferrying the raw ingredients for life across vast distances. In this scenario, the emergence of life is not confined to individual planetary systems, but is a galactic phenomenon, facilitated by the very same processes that scatter debris into the void. This perspective raises profound questions about the universality of life. If interstellar objects serve as vectors for biological material, they might explain why certain organic compounds are found in meteorites and comets throughout the solar system. For example, the Murchison meteorite, which fell in Australia in 1969, contains over 70 amino acids, many of which are not produced by terrestrial life. Some researchers speculate that such materials could have been delivered by interstellar visitors, their frozen vaults preserving complex chemistry from distant star systems. If this is true, then the line between native and foreign becomes blurred. Life on Earth may owe its origins, in part, to the silent passage of these cosmic travelers, whose icy exteriors conceal the secrets of distant worlds. Beyond their role in distributing organic material, interstellar objects also challenge our assumptions about the rarity of habitable environments. The fact that such objects can travel between star systems implies that planetary systems are not static islands, but active participants in a larger cosmic ecosystem. When a planet is ejected from its system, perhaps due to gravitational interactions with a gas giant, it carries with it the potential for life, if any exists there. This raises the possibility of interstellar migration, where organisms or their genetic material might survive the harsh journey through space. While the survival of microbes in the vacuum of space remains debated, experiments aboard the International Space Station have shown that certain extremophiles can endure prolonged exposure to cosmic radiation and extreme temperatures. If such hardy life forms exist elsewhere in the galaxy, they could hitch a ride on interstellar objects, seeding new planets with the spark of biology. Yet the implications of interstellar objects extend beyond the biological realm. Their existence compels us to confront the scale and complexity of the universe. Consider that Oumuamua likely originated in a star system located hundreds of light years away, perhaps in the direction of the bright star Vega. The journey of such an object across interstellar space would take tens of thousands of years, during which it would traverse regions of the galaxy teeming with stars, nebulae, and gravitational anomalies. The fact that it arrived at our doorstep at all is a testament to the sheer volume of interstellar debris that must exist, though most of it remains undetected due to the vastness of space. This realization underscores the humility required to study the cosmos. For every object we observe, countless others remain hidden, their stories waiting to be uncovered. The search for interstellar objects also intersects with the quest for extraterrestrial intelligence. While there is no evidence to suggest that these wanderers are artificial constructs, their enigmatic nature has inspired speculation about more exotic possibilities. Could a highly advanced civilization have engineered such objects as probes or messages? The idea is not far-fetched when one considers the challenges of interstellar travel. Sending a spacecraft to another star system requires immense energy and time, but launching an object in the opposite direction, using the gravitational slingshot effect, might be a simpler way to disperse information or technology. This concept, sometimes referred to as von Neumann probes, envisions self-replicating machines that could spread across the galaxy, leaving behind traces of their creators. While Oumuamua's natural origin is widely accepted, the lack of direct evidence for artificiality means the door remains open to alternative interpretations. Even in the absence of definitive proof, the mere possibility of intelligent involvement in the cosmos reshapes our worldview. The detection of interstellar objects forces us to confront the Fermi paradox, the question of why, given the vastness of the universe, we have yet to encounter clear signs of extraterrestrial life. One hypothesis is that life is rare, but another is that it is so common that its influence is subtle or indirect. If interstellar objects are indeed the footprints of advanced civilizations, Their study could yield insights into the technological capabilities of others. Alternatively, if they are purely natural phenomena, they still serve as a reminder that the universe is far more intricate and interconnected than we have imagined. Either way, the pursuit of understanding these wanderers is a step toward unraveling the mysteries of existence. As we continue to refine our observational techniques and expand our reach into the cosmos, the study of interstellar objects promises to deepen our connection to the universe. These silent travelers, born in the crucibles of distant stars and scattered by the gravitational tides of space, are more than scientific curiosities. They are reminders of the shared history of all matter in the galaxy, the echoes of cosmic events that predate the formation of our own solar system. In their passage, they carry the potential to answer fundamental questions about the origins of life, the prevalence of habitable worlds, and the ultimate fate of civilizations that may one day bridge the chasm between the stars. As we turn our gaze inward from the interstellar void, the universe reveals another frontier of mystery, a frigid, distant realm that lies just beyond the orbit of Neptune, known as the Kuiper Belt. This vast reservoir of icy bodies is the birthplace of many comets and a treasure trove of primordial material left over from the formation of the solar system. Unlike the interstellar wanderers that arrive from the depths of space, the Kuiper Belt's inhabitants are deeply rooted in our cosmic neighborhood, their orbits shaped by the gravitational dance of the outer planets. Yet, despite their local origin, these objects share a kinship with their interstellar counterparts in their role as time capsules, preserving the chemical and physical imprints of the solar system's earliest days. The Kuiper Belt is a testament to the dynamic history of our solar system, composed primarily of frozen volatiles like water, methane, and ammonia. Its members range in size from small, irregularly shaped objects to dwarf planets like Pluto and Eris. These bodies, often referred to as trans-Neptunian objects, TNOs, are remnants of the protoplanetary disk that once swirled around the young sun. As the giant planets migrated and settled into their current orbits, many of these icy bodies were either incorporated into the planets or flung outward to form the Kuiper Belt. Today, they drift in a cold, slow-motion ballet, their surfaces untouched by the heat of the inner solar system. Studying them offers a unique opportunity to peer into the past, to understand the conditions that gave rise to the planets we see today. Just as interstellar objects provide insights into the formation of distant star systems, the Kuiper Belt serves as a laboratory for studying the processes that shaped our own. The similarities between Kuiper Belt objects and comets like 2I Borisov suggest that both interstellar and native icy bodies may share common origins, their materials forged in the same cosmic crucibles. However, the Kuiper Belt's proximity allows for more detailed observation, and in some cases, direct exploration. Missions like NASA's New Horizons, which flew by Pluto in 2015, and the TNO Arrokoth in 2019, have begun to unravel the secrets of this remote region. These missions have revealed that many Kuiper Belt objects are binaries or have complex shapes, hinting at the violent collisions and mergers that occurred during the solar system's youth. The Kuiper Belt also holds clues to the ongoing evolution of the solar system. Gravitational interactions with Neptune and the hypothetical planet 9, a yet undiscovered massive planet believed to reside in the outer solar system, continue to shape the orbits of Kuiper Belt objects. Some are nudged into the inner solar system, becoming the comets that streak across our skies, while others are ejected into the even more distant Oort Cloud, a spherical shell of icy bodies that marks the solar system's outermost boundary. This continuous exchange between the Kuiper Belt, the Oort Cloud, and the inner solar system underscores the interconnectedness of all regions of space. Even as we seek to understand the origins of interstellar objects, we must remember that our own backyard is just as rich in unanswered questions. By exploring the Kuiper Belt, we are not only tracing the history of our solar system, but also gaining a deeper appreciation for its place in the cosmos. The icy bodies that dwell in this distant realm are the echoes of the same cosmic processes that give rise to interstellar wanderers. They remind us that the universe is not a collection of isolated systems, but a vast evolving network of matter and energy, where the past is preserved in frozen fragments and the future is shaped by the relentless motion of gravity. As we venture farther into the Kuiper Belt, we step closer to understanding the threads that bind the solar system to the wider galaxy, a journey that begins with the recognition that every object, whether born here or borrowed from the stars, is part of a grander story. Beyond the orbit of Neptune, where sunlight dims to a faint glimmer and temperatures plummet to near absolute zero, lies a vast, silent frontier, the Kuiper Belt. This distant region, often described as a donut-shaped ring of icy debris, stretches over 2 billion miles across the solar system's outer reaches. It is a realm of frozen relics, a cosmic museum preserving the raw materials from which planets were born. While Pluto once reigned as the archetype of this domain, the Kuiper Belt is far more than a single world. It is a dynamic, teeming expanse of dwarf planets, comets, and asteroid-like bodies, each whispering tales of the solar system's tumultuous infancy. To gaze outward toward the Kuiper Belt is to peer into a time capsule. These objects, untouched for billions of years, hold secrets about the forces that shaped our celestial neighborhood. They are not mere static remnants, but active participants in the solar system's ongoing dance of gravity and motion. The Kuiper Belt's position, just beyond Neptune's gravitational influence, makes it a critical boundary between the inner and outer solar system. Here, the echoes of planetary migrations and chaotic collisions remain etched in the orbits and compositions of its inhabitants. Yet, despite its importance, this region remains enigmatic, a place where new discoveries challenge old assumptions and where mysteries still abound. What lies within this frozen frontier? Why do certain objects orbit in strange, tilted paths? And what might they reveal about the solar system's uncharted past? The Kuiper Belt is not a cosmic backwater, but a vibrant, evolving tapestry of celestial history. As we journey into its depths, we uncover not only the origins of our own planet, but also the potential for hidden wonders yet to be discovered. The Kuiper Belt spans a distance of 30 to 50 astronomical units, AU, from the Sun, placing it far beyond Neptune's orbit. To grasp this scale, imagine stretching a football field from goalpost to goalpost. The Sun would sit at one end, and Neptune would be somewhere near the 30-yard line. The Kuiper Belt extends well beyond the 40-yard mark.
Sorry.
A vast,
No,
diffuse
please,
expanse
go
where
ahead.
sunlight
Take a
takes
look.
hours to reach, and where temperatures hover around 120 Decode.
Today is
when
full moon, so I try to
470
take some
verse
picture and
Saturn.
videos.
Within this frigid realm, objects orbit the Sun in diverse trajectories, shaped by the gravitational tug-of-war between Neptune and the unseen forces of the early solar system. Unlike the orderly asteroid belt between Mars and Jupiter, the Kuiper Belt is a dynamic crucible of motion. Its inhabitants range from dwarf planets like Pluto and Eris to tiny comet-like nuclei just a few kilometers wide. Many of these objects are classical Kuiper Belt objects, KBOs, which follow nearly circular orbits aligned with the plane of the solar system. Others, known as resonant KBOs, are locked in gravitational harmony with Neptune, for instance. Pluto itself resides in a 3-2 orbital resonance, completing 2 laps around the Sun for every 3 of Neptune's. Beyond these lie scattered disk objects, whose highly elliptical orbits suggest violent ejections from deeper within the Kuiper Belt, likely due to Neptune's outward migration during the solar system's youth. The New Horizons mission, launched in 2006, revolutionized our understanding of this region. When it flew by Pluto in 2015, it unveiled a world of startling complexity: glaciers of nitrogen ice, towering mountains of water ice, and a heart-shaped plain named Sputnik Planitia, where cryovolcanic activity hinted at internal heat. These findings shattered the stereotype of KBOs as inert, icy rocks. Instead, they revealed geologically active worlds capable of harboring subsurface oceans and dynamic weather systems. In 2019, New Horizons' flyby of the ancient KBO Arakoth, dubbed Ultima Thule at the time, provided further insight. Arakoth's contact binary shape, resembling a snowman, suggested it formed through a gentle collision of 2 smaller bodies, offering a rare glimpse into the birth of planetary building blocks. The Kuiper Belt contrasts starkly with the Oort Cloud, a more distant spherical reservoir of icy bodies that extends up to 100,000 AU from the Sun. While the Oort Cloud is believed to be the source of long-period comets, the Kuiper Belt fuels short-period comets that return every few decades. This distinction underscores the Kuiper Belt's role as a more immediate, structurally distinct region, one that interacts closely with the giant planets and reflects the solar system's recent evolutionary history. Studying the Kuiper Belt is akin to deciphering a cosmic ledger of planetary migration. Modern theories, such as the Nice model, propose that the giant planets did not form in their current positions, but instead migrated through gravitational interactions with surrounding material. Neptune, in particular, is thought to have drifted outward, scattering icy bodies into the Kuiper Belt, and even farther into the Oort Cloud. The peculiar orbital patterns of many KBOs, such as those with extreme tilts or high eccentricities, serve as fossilized evidence of this chaotic past. By mapping these orbits, astronomers reconstruct the solar system's turbulent adolescence, revealing how planets reshaped their neighborhood and redistributed volatile materials like water and organic compounds. One of the most tantalizing mysteries is the potential existence of a massive, undiscovered planet lurking within the Kuiper Belt, dubbed Planet 9. This hypothetical world, estimated to be 10 times Earth's mass and orbiting hundreds of AU from the Sun, could explain the curious alignment of distant KBOs. Observations show that several objects with highly inclined orbits cluster in a way that suggests they are being gravitationally herded by an unseen body. If confirmed, Planet 9 would not only validate models of planetary migration, but also redefine our understanding of the solar system's architecture. Yet the search for this elusive giant remains ongoing, with surveys combing the sky for a faint glint against the backdrop of stars. Even without Planet 9, the Kuiper Belt holds profound implications for the distribution of life's ingredients. Many KBOs contain complex organic molecules, including methanol and amino acids precursors, hinting at a rich chemical inventory preserved since the solar system's dawn. These volatiles may have been delivered to Earth via comets, seeding the conditions for life. By analyzing KBOs, scientists trace the pathways by which essential elements were transported across the solar system, illuminating how habitable worlds like ours came to exist. Moreover, the Kuiper Belt challenges our definitions of planetary classification. Pluto's reclassification as a dwarf planet in 2006 sparked debates about what constitutes a planet, highlighting the diversity of worlds in this region. With over 2,000 known KBOs and thousands more awaiting discovery, the Kuiper Belt reminds us that the solar system is not a static collection of neatly categorized objects, but a dynamic, evolving ecosystem. As the Kuiper Belt's icy denizens drift in their eternal orbits, some are destined for dramatic journeys, gravitational nudges from Neptune, or perhaps the unseen hand of Planet 9 can dislodge these frozen wanderers, sending them hurtling inward toward the sun. What begins as a tranquil existence in the outer dark ends in a fiery rebirth as a comet. These celestial nomads, glowing with dust and gas, become visible spectacles in our skies, their tails trailing across the heavens like ancient messengers from the edge of space. Comets are more than fleeting beauty. They are time capsules of the solar system's earliest days. Their composition, forged in the cold depths of the Kuiper Belt, offers clues about the materials that coalesce to form planets. In the next segment, we will explore the life cycle of a comet, tracing its path from icy relic to luminous phenomenon, and uncovering the secrets it carries from the solar system's distant past. In the velvet expanse of the night sky, a comet glides, a luminous spectre trailing a ghostly plume of gas and dust. To the untrained eye, it may seem a fleeting marvel, a celestial firework destined to vanish. But to those who peer beyond its ethereal glow, a comet is far more than a transient phenomenon. It is a relic of the solar system's birth, a preserved fragment of a time when the cosmos was young and the planets were still forming. These wanderers, born in the frigid outer reaches of our neighborhood, carry within their icy cores the raw materials of existence: frozen water, primordial dust, and complex organic molecules. When a comet approaches the sun, its fragile heart begins to unravel, releasing particles that have lain undisturbed for billions of years. In doing so, it becomes both a time machine and a storyteller, offering glimpses into an epoch when the solar system was a swirling nursery of chaos and creation. To study comets is to peer into a cosmic archive, one that holds clues to the origins of life itself. Yet for all their beauty, comets remain enigmatic. Their trajectories are erratic, their appearances unpredictable. Some return with clockwork precision, like Halley's Comet, which has visited Earth every 76 years since the time of the ancient Greeks. Others arrive once in millennia, their paths shaped by unseen forces at the solar system's edge. What drives these celestial vagabonds from the abyssal cold of the Kuiper Belt and the distant Oort Cloud? How do their icy surfaces conceal secrets about the conditions that gave rise to the planets, the oceans, and perhaps even the building blocks of life? As we trace the arc of a comet's journey from the depths of space to the warmth of the sun, we uncover a narrative of survival and transformation, one that bridges the chasm between the primordial past and the present-day cosmos. Comets are often described as cosmic snowballs, a poetic yet apt characterization of their composition. At their core lies a nucleus, a dense, irregularly shaped body, composed of a mixture of water ice, frozen gases such as carbon dioxide and methane, and a fine layer of dark carbon-rich dust. This amalgamation, known colloquially as a dirty snowball, is a remnant of the protoplanetary disk, the vast rotating cloud of gas and dust that once surrounded the infant sun. As the solar system coalesced some 4.6 billion years ago, regions closer to the sun warmed sufficiently for ices to vaporize, leaving behind the rocky metallic planets. Farther out, in the colder realms beyond Neptune, temperatures remained low enough for volatile substances to condense, giving rise to the icy bodies that now populate the Kuiper Belt and the Oort Cloud. Here, comets formed through a process of gentle gravitational accretion, their components sticking together without the intense collisions that shaped the terrestrial worlds. The distinction between short-period and long-period comets hinges on their orbital characteristics. Short-period comets, with orbital periods under 200 years, originate in the Kuiper Belt, a toroidal region of icy objects extending from the orbit of Neptune to approximately 50 astronomical units, AU, from the Sun. These comets follow relatively stable, elliptical orbits and are often perturbed by the gravitational influence of Neptune, sending them inward on journeys that bring them within the inner solar system. Long-period comets, by contrast, hail from the Oort Cloud, a hypothetical spherical shell of icy bodies that extends up to 100,000 AU from the Sun, far beyond Pluto's orbit. Their orbits are highly eccentric, and their paths can take tens of thousands of years to complete. Unlike their shorter-lived counterparts, long-period comets are thought to be nudged into the inner solar system by external forces, such as the gravitational pull of passing stars or the Milky Way's own tidal forces. When a comet ventures close enough to the Sun, its surface begins to warm, triggering a dramatic transformation. The process of sublimation, the direct transition of solid ice to gas, releases jets of material that form a glowing halo around the nucleus, known as the coma. Solar radiation and the solar wind then push these particles away, creating the iconic tail that always points away from the Sun. A comet typically develops two distinct tails: a blue ion tail composed of ionized gases, which is straight and aligned with the solar wind, and a yellowish dust tail, which curves gently due to the slower movement of larger particles. These features, though transient, are among the most visually arresting phenomena in the night sky, serving as a testament to the dynamic interplay between a comet's fragile constitution and the Sun's relentless energy. The European Space Agency's Rosetta mission, which rendezvoused with Comet 67P Churyumov-Gerasimenko in 2014, provided unprecedented insights into these processes. By deploying the Philae lander onto the comet's surface, scientists were able to analyze its chemical makeup in situ. Among the discoveries was the presence of complex organic molecules, including glycine, an amino acid essential to life, and phosphorus, a key component of DNA and cellular membranes. These findings reinforce the hypothesis that comets may have played a pivotal role in delivering the building blocks of life to the early Earth. Moreover, the mission revealed that the comet's nucleus was riddled with voids and fractures, suggesting a formation history marked by gentle accumulation rather than violent collision. Such observations underscore the delicate, almost fragile nature of comets, which are as much archives of the past as they are vulnerable to the forces of the present. The implications of cometary science extend far beyond the realm of astronomy. They touch upon the very foundations of biology and planetary evolution. One of the most tantalizing questions in modern science is whether comets contributed to the emergence of life on Earth. The idea, known as panspermia, posits that the seeds of life were delivered to our planet via extraterrestrial sources, including comets and asteroids. While this theory remains speculative, evidence from cometary missions and laboratory analyses of meteorites suggest that the necessary ingredients for life, water, amino acids, and other organic compounds were indeed present in the early solar system. For instance, the detection of glycine and other prebiotic molecules on Comet 67P hints at the possibility that comets acted as cosmic couriers, ferrying these materials to the nascent Earth during the late heavy bombardment, a period of intense meteorite impacts around 4 billion years ago. Water, the universal solvent essential to all known forms of life, is another element whose extraterrestrial origin has been linked to comets. While Earth's oceans could have formed through volcanic outgassing or the release of water trapped in the planet's mantle, the isotopic composition of Earth's water appears to align more closely with that found in certain comets. Specifically, the ratio of deuterium to hydrogen in Earth's oceans matches that observed in comets from the Oort Cloud, such as 103P Hartley 2. This similarity suggests that comets may have supplemented Earth's water supply, particularly during the planet's early history when its surface was molten and inhospitable. However, the story is not straightforward. Recent studies of the Rosetta mission data indicate that the deuterium to hydrogen ratio in Comet 67P differs significantly from that of Earth's water, complicating the narrative. These discrepancies highlight the complexity of tracing Earth's water origins and underscore the need for further exploration of diverse cometary samples beyond their potential role in seeding life. Comets also serve as time capsules of the protoplanetary disk's conditions. Because they formed in the cold, distant reaches of the solar system, their compositions reflect the chemical and physical environment of that era. For example, the presence of refractory minerals, materials that require high temperatures to form, within cometary nuclei challenges the assumption that these bodies originated solely in the frigid outer solar system. This paradox is explained by models proposing that the protoplanetary disk was a dynamic place, with material transported across vast distances by turbulent flows and magnetic fields. Such mixing would have allowed high-temperature minerals to migrate outward before freezing, preserving them in comets like tiny relics of a hotter past. These findings suggest that the early solar system was not a static, orderly process, but a chaotic, ever-shifting cauldron of energy and motion. The volatile nature of comets themselves mirrors this dynamism. Unlike the stony asteroids that dominate the inner solar system, comets are inherently unstable. Their surfaces are prone to sudden eruptions, triggered by the uneven heating of their irregular shapes. These eruptions can create plumes of gas and dust that temporarily alter the comet's trajectory, a phenomenon observed in missions like Deep Impact, which deliberately collided with Comet Tempel 1 to study its interior. Additionally, comets can fragment entirely, as seen in the case of Comet Shoemaker-Levy 9, which broke apart into multiple fragments before colliding with Jupiter in 1994. Such events remind us that the solar system is not a tranquil haven, but a theater of constant change, where gravitational interactions, collisions, and internal stresses shape the fates of celestial bodies. This duality of preservation and destruction is central to the story of comets. They are both fragile and resilient, their icy hearts enduring for eons, while their surfaces are constantly reshaped by the sun's heat. They are messengers of the past, yet their journeys are dictated by the same forces that govern the future. In studying them, we gain not only knowledge of the solar system's origins, but also a deeper appreciation for the interconnectedness of cosmic processes. Each comet is a thread in the tapestry of the universe, linking the birth of stars to the emergence of life, the dance of planets to the chaos of impact. As comets embark on their pilgrimages from the distant Oort Cloud, they are not solitary travelers. Their journeys are orchestrated by invisible hands, gravitational tides, and stellar encounters that reach deep into the solar system's periphery. The Oort Cloud, a vast hypothetical sphere of icy bodies encircling the Sun at a distance of trillions of kilometers, exists in a delicate equilibrium. Here, the Sun's gravity is barely perceptible, and the influence of neighboring stars and the Milky Way's galactic plane looms large. These external forces act as cosmic shepherds, nudging comets off their stable orbits and sending them spiraling inward on trajectories that will eventually bring them into the Sun's embrace, or occasionally into catastrophic collisions with planets. Consider the passage of a rogue star through the solar system's outermost reaches. Though such events are rare, occurring roughly once every few million years, their effects are profound. A star's gravitational field, even at a distance, can perturb the orbits of Oort Cloud objects, compressing the cloud and increasing the likelihood of a comet escaping its confines. Similarly, the Milky Way's tidal forces, the differential pull of gravity across different parts of the solar system, exert a slow, inexorable influence. As the solar system orbits the galactic center, its position relative to the galactic plane shifts, causing periodic fluctuations in the Oort Cloud stability. These fluctuations may explain the observed periodicity in comet arrivals, a pattern that some researchers link to mass extinction events on Earth. Yet, the most dramatic disruptions arise not from the galaxy's gentle tides, but from chance encounters. A passing star, a wandering giant planet ejected from another system, or even a rogue black hole could send shockwaves through the Oort Cloud, scattering comets like pebbles in a storm. Such scenarios, while rare, underscore the solar system's vulnerability to the vast, unseen forces that govern the cosmos. The comets that emerge from these disturbances are not merely visitors, they are harbingers of the solar system's dynamic, ever-changing relationship with the universe at large. As we turn our gaze to the next chapter in this cosmic narrative, we must consider the broader implications of these celestial interactions. How do these external forces shape the distribution of comets over time? What can their arrival patterns reveal about the structure of the galaxy and the history of the solar system's motion within it? And perhaps most intriguingly, do these same forces play a role in the long-term stability of our planetary neighborhood? The answers lie in the delicate balance between order and chaos, a theme that will unfold as we explore the intricate web of gravitational influences that bind the solar system to the cosmos. In the next segment, we will delve into the mechanics of these gravitational tugs, examining how the Sun's neighbors and the Milky Way itself conspire to stir the Oort Cloud into action. We will uncover the hidden architecture of the solar system's outskirts and the ways in which its cometary population serves as a barometer for the universe's grandest forces. For now, however, let us linger in the quiet majesty of comets, those ancient wanderers whose journeys are etched in the very fabric of time. Far beyond the orbit of Neptune, where sunlight dims to an ethereal whisper, lies the Oort Cloud, a vast spherical reservoir of icy bodies that marks the outermost boundary of our solar system. This region, named after Dutch astronomer Jan Oort, is a relic of the solar system's formation, a frozen archive of primordial material left over from the collapse of a molecular cloud nearly 5 billion years ago. The Oort Cloud stretches trillions of kilometers into space, its inner edge nestled at about 2,000 astronomical units (AU) from the Sun, while its outer limits may extend to 100,000 AU or more. To put this in perspective, even the fastest human-made spacecraft would take tens of thousands of years to reach the cloud's core. Yet, despite its remoteness, the Oort Cloud is anything but silent. It is a dynamic frontier, constantly stirred by the gravitational ripples of passing stars and the subtle pull of the Milky Way itself. Imagine, if you will, the Oort Cloud as a delicate, invisible web spun across the cosmos. Each thread represents the gravitational bond between the Sun and its distant icy companions, comets, dwarf planets, and other frozen wanderers. These objects, often no larger than a mountain, drift in near perpetual isolation, their orbits shaped by the faint tug of the Sun and the even fainter influence of other celestial bodies. But this equilibrium is fragile. Occasionally, a passing star brushes against the edge of this web, its own gravity distorting the threads like the ripple from a stone cast into a pond. Such encounters, though rare, can send shockwaves through the Oort Cloud, dislodging comets from their ancient slumber and hurling them inward on trajectories that could intersect with the inner solar system. This cosmic interplay is not merely a curiosity. It is a testament to the interconnectedness of the universe. The Oort Cloud, though remote, is not isolated. It exists within a galactic neighborhood teeming with motion, where stars migrate, collide, and drift apart over eons. The Milky Way is a living, breathing entity, and the Oort Cloud is its most sensitive limb, reacting to the gravitational pulses of passing stars and the slow, inexorable pull of the galaxy's tidal forces. To study these phenomena is to glimpse the hidden choreography of the cosmos, a dance of immense scales and unfathomable time spans, where even the smallest perturbation can reverberate through the fabric of space. The gravitational interactions that perturb the Oort Cloud are governed by the same fundamental laws that dictate the motion of planets and moons: Newton's law of universal gravitation and Einstein's general theory of relativity. When a star passes near the solar system, its gravity exerts a force on the Oort Cloud's icy inhabitants, subtly altering their orbits. These disruptions are not instantaneous collisions, but rather gentle tugs that accumulate over time. A star traveling at typical galactic speeds, tens of kilometers per second, might pass within a few parsecs, about 10-30 light-years of the Sun, a distance close enough to perturb the Oort Cloud, but far enough to avoid catastrophic damage to the inner planet. One of the most well-documented examples of such an encounter is the passage of Skols's star, a dim red dwarf and brown dwarf binary system that approached the solar system approximately 70,000 years ago. Though it came no closer than 0.5 parsecs, roughly 1.6 light-years, its gravitational influence was sufficient to perturb the outer edges of the Oort Cloud. Astronomers estimate that such stellar flybys occur roughly once every 100,000 to 1 million years, depending on the density of the local galactic neighborhood. Each encounter acts like a cosmic wake-up call, nudging comets into new orbital paths. Some of these objects remain bound to the Sun, entering highly elliptical orbits that bring them perilously close to the inner solar system. Others are ejected entirely, becoming rogue bodies adrift in the galaxy. Beyond individual stellar encounters, the Milky Way itself exerts a slower, more pervasive influence on the Oort Cloud. Galactic tides, the differential gravitational pull of the galaxy on different parts of the solar system, act as a kind of cosmic tide pool, stretching and compressing the Oort Cloud over millions of years. As the solar system orbits the galactic center every 250 million years, it oscillates vertically above and below the galactic plane, experiencing varying gravitational forces. These oscillations create periodic distortions in the Oort Cloud, akin to the way ocean tides rise and fall under the moon's influence. Computer simulations suggest that these galactic tides, combined with stellar perturbations, may be responsible for triggering comet showers, epochs during which the rate of comets entering the inner solar system increases dramatically. The consequences of these perturbations are profound. Long-period comets, which originate in the Oort Cloud and have orbital periods exceeding 200 years, are particularly susceptible to gravitational nudges. When a passing star or galactic tide alters their trajectory, these comets can descend toward the Sun, their surfaces warmed by solar radiation and their tails glowing with reflected light. In some cases, their paths cross with those of planets, raising the possibility of impacts. While most comets burn up harmlessly in the atmosphere, larger ones pose a threat to planetary ecosystems. The frequency of such events is low, but their potential impact is immense, as evidenced by the scars etched into Earth's geological record. The gravitational disruptions of the Oort Cloud are not mere academic curiosities. They are deeply intertwined with the history of life on Earth. Paleontologists and geologists have uncovered evidence of massive comet and asteroid impacts throughout Earth's past, including the Chicxulub impactor that contributed to the extinction of the dinosaurs 66 million years ago. While the majority of these impacts originated from the asteroid belt, a significant fraction, perhaps as many as 10%, are believed to have come from the Oort Cloud. This suggests that stellar perturbations and galactic tides may play a role in shaping the biosphere over geological timescales. The connection between cosmic events and biological evolution is both humbling and awe-inspiring. Life on Earth has endured countless cataclysms, adapting to shifting climates, rising seas, and the occasional extraterrestrial collision. The Oort Cloud, in this sense, is not just a repository of ice and rock. It is a cosmic sieve, filtering the raw materials of destruction and creation into the cradle of life. Every comet that ventures inward carries with it the building blocks of organic molecules, some of which may have contributed to the origins of life itself. In this way, the same forces that threaten Earth also sustain it, a paradox that underscores the intricate balance of the universe. Yet the implications of these gravitational tugs extend beyond our planet. They reveal the Milky Way as a vast, interconnected web of influence, where the fates of stars and planets are inextricably linked. A single star's passage can ripple through the Oort Cloud, setting off a cascade of events that may alter the trajectory of a comet destined to strike another world. In this galactic tapestry, every thread is connected, and every disturbance sends vibrations through the cosmic loom. This perspective challenges the notion of individuality in the cosmos, reminding us that even the most isolated regions of space are part of a greater whole. Looking ahead, the question arises, could a future stellar encounter pose a threat to Earth? While the probability is low, stellar passages capable of perturbing the Oort Cloud occur on timescales of hundreds of thousands to millions of years. The potential consequences are impossible to ignore. Astronomers monitor the sky for rogue stars and other celestial wanderers, but predicting the exact timing and trajectory of a perturbation remains a formidable challenge. Even if such an event were detected decades or centuries in advance, humanity's ability to mitigate its effects would depend on our technological prowess and global cooperation. In the grand scheme of cosmic history, however, these disruptions are fleeting moments in an eternal cycle of creation and transformation. To fully grasp the significance of these gravitational tugs, we must rewind the cosmic clock and examine the origins of the Oort Cloud itself. How did this vast icy reservoir form? What processes scattered its inhabitants to such staggering distances? The answers lie in the early history of the solar system, a time when planets were still coalescing from a swirling disk of gas and dust, and gravitational chaos reigned supreme. By tracing the Oort Cloud's formation, we can better understand why it is so vulnerable to external influences, and what it reveals about the dynamic nature of our galactic neighborhood. In the next segment, we will journey back to the dawn of the solar system, exploring the theories that seek to unravel the mysteries of its outermost frontier. This script balances scientific rigor with poetic imagery, inviting readers to contemplate the universe's vastness and the delicate balance that sustains it. Each section flows into the next, maintaining a narrative thread that connects cosmic phenomena to terrestrial implications. Imagine a realm so distant that sunlight takes centuries to reach it, a place where the gravitational pull of the sun is weaker than the gentle tug of passing stars. This is the Oort Cloud, a vast, invisible shell of icy remnants that encircles our solar system like a cosmic halo. Though no telescope has yet glimpsed its true form, its presence is inferred through the comets that occasionally fall toward the inner solar system, glowing as fleeting fireflies against the night sky. These comets are more than mere wanderers. They are messengers from the solar system's infancy, relics of a time when planets were not yet settled in their current orbits. To understand the Oort Cloud is to unravel a story etched in the scars of celestial chaos, a story of gravitational slingshots, planetary migrations, and the quiet persistence of time. How did a diffuse shell of icy debris come to encircle our solar system? The answer lies buried in the tumultuous history of the solar system's youth, a period marked by collisions, upheaval, and the slow, inexorable dance of gravity. Let us journey backward in time, to an era when the solar system was a swirling maelstrom of dust, rock and ice, and witness the birth of the Oort Cloud, a testament to the universe's capacity to transform disorder into structure. The Oort Cloud is not a static relic, but the product of a dynamic interplay between gravity and time. Its formation can be traced to the earliest chapters of the solar system's history, when the planets were still forming and the young sun was surrounded by a protoplanetary disk teeming with planetesimals, chunks of ice, rock and metal, ranging from pebbles to mountains. In this primordial environment, the gas giants Jupiter, Saturn, Uranus and Neptune were not yet in their current positions. Instead, they migrated inward and outward in a chaotic waltz, their immense gravitational fields acting as cosmic shepherds and marauders alike. As these giants shifted their orbits, their gravitational influence sent ripples through the disk, scattering planetesimals like leaves in a storm. The key to the Oort Cloud's formation lies in the gravitational slingshot effect. When a planetesimal ventured too close to a gas giant, the planet's gravity could either capture it into a new orbit or hurl it into the void. Some of these ejected bodies traveled far enough from the Sun that its gravitational hold weakened to near insignificance. Here, in the outer reaches of the solar system, the planetesimals entered a liminal space, where the Sun's gravity was feeble compared to the tidal forces of the Milky Way galaxy and the occasional gravitational nudge from passing stars. Over millions of years, these external forces reshaped the trajectories of the scattered bodies, stretching their orbits into a vast spherical cloud. This process, known as dynamical evolution, is the cornerstone of modern theories about the Oort Cloud's origin. Computer simulations have been instrumental in modeling this process. By inputting the known masses and motions of the gas giants, scientists can track how planetesimals would have behaved under their gravitational influence. These simulations reveal that over tens of millions of years, a significant fraction of the original disk's material was ejected to distances of up to 100,000 astronomical units, AU, from the Sun. At such distances, the Oort Cloud exists as a transitional zone between the solar system and the interstellar medium, a region where the Sun's gravity is barely perceptible. The cloud is thought to contain trillions of objects, most too small and faint to detect individually, but collectively forming a reservoir of frozen history. Yet the story does not end with ejection. The Oort Cloud's spherical shape is not static, but shaped by the subtle gravitational perturbations of the galaxy itself. The Milky Way's spiral arms and the gravitational pull of nearby stars act as invisible sculptors, nudging the orbits of the cloud's inhabitants. Occasionally, a passing star or a rogue planet from another system might send a ripple through the cloud, dislodging a comet onto a trajectory toward the inner solar system. These rare events bridge the gap between the Oort Cloud and the familiar world of planets, reminding us that even the most distant corners of our solar system are connected to the greater cosmic web. The Oort Cloud's existence is more than a curiosity. It is a critical piece of the puzzle in understanding how planetary systems evolve. Its formation is deeply tied to the NICE model, a widely accepted theory that posits the gas giants underwent a dramatic migration phase in the early solar system. According to this model, Jupiter and Saturn initially formed closer to the Sun, their gravitational interactions destabilizing the orbits of Uranus and Neptune. This triggered a cascade of events. The outer planets scattered planetesimals, which in turn disrupted the orbits of the gas giants themselves. The resulting chaos culminated in the planets settling into their current, more stable configuration. The Oort Cloud in this framework is not just a byproduct of planetary formation, but a direct consequence of the solar system's turbulent adolescence. This theory carries profound implications for the broader field of astrophysics. If the Oort Cloud arose from the gravitational turmoil of the early solar system, it stands to reason that other planetary systems may harbor similar structures. Observations of exoplanets have revealed that many systems exhibit signs of past instability, such as misaligned orbital planes or planets parked in highly eccentric orbits. These features suggest that planetary migrations and the subsequent scattering of debris are not unique to our solar system, but a common feature of cosmic evolution. Just as the Oort Cloud preserves the memory of our solar system's youth, hypothetical Oort-like clouds around other stars could serve as archives of their own histories. Such discoveries would deepen our understanding of how planetary systems form and evolve, offering clues about the prevalence of life-supporting conditions in the universe. However, the Oort Cloud remains shrouded in uncertainty. One of the most pressing questions is the total mass of the cloud. While estimates suggest it contains up to 1 trillion comets, the exact number and distribution of objects remains speculative. Astronomers debate whether the cloud's mass was primarily derived from our solar system's own protoplanetary disk, or if a fraction of its icy bodies were captured from neighboring stars during the solar system's early years. This latter possibility introduces a fascinating twist. The Oort Cloud might not be entirely indigenous, but a hybrid structure, forged by both internal and external influences. Recent studies using advanced telescopes like the James Webb Space Telescope have begun to probe the chemical composition of comets, offering indirect insights into the cloud's origins. If future missions detect isotopic signatures matching those of interstellar objects, it would confirm the cloud's extraterrestrial roots, a cosmic exchange of debris between fledgling planetary systems. Another mystery lies in the Oort Cloud's role in the delivery of volatile materials to the inner solar system. Comets, born of ice and dust, are believed to have played a crucial role in seeding Earth with water and organic compounds. By studying the composition of these ancient visitors, scientists hope to reconstruct the conditions of the early solar system and trace the pathways that brought life's ingredients to our planet. The Oort Cloud in this context becomes more than a graveyard of planetary leftovers. It is a bridge between the past and present, a repository of information about the processes that shaped habitability. As such, its study is not merely an exercise in planetary science, but a quest to understand the origins of life itself. Despite decades of research, the Oort Cloud continues to defy direct observation. Its inhabitants are too dim, its distance is too vast, and its structure too diffuse for current technology to resolve. Yet the absence of visual confirmation has not hindered progress. Instead, it has spurred innovation. New methods such as analyzing the orbits of long-period comets and searching for gravitational anomalies caused by the cloud's mass offer indirect ways to map its extent. Future missions, perhaps even interstellar probes capable of detecting faint signals from the cloud's outskirts, may one day pierce the veil of this distant frontier. Until then, the Oort Cloud endures as a symbol of the universe's ingenuity, the ability to take fragments of chaos and weave them into a structure that spans light years, a silent guardian of the solar system's secrets. As we contemplate the Oort Cloud's role in shaping the solar system, a deeper question emerges. What unseen forces might govern this distant realm? The cloud's stability and evolution are influenced not only by the gravitational tugs of stars and planets, but also by phenomena that lie beyond the reach of conventional observation. Among these, one force looms large in the annals of astrophysics, a cosmic enigma that neither emits light nor interacts with ordinary matter in discernible ways. Known as dark matter, this mysterious substance permeates the universe, its gravitational pull binding galaxies together while remaining invisible to our instruments. Could dark matter, too, play a role in the dynamics of the Oort Cloud? And if so, what might this reveal about the fundamental architecture of the cosmos? Let us now turn from the icy fringes of the solar system to the shadowy scaffolding of the universe itself, and explore the profound implications of dark matter's hidden hand. In the vast expanse of the universe, where light-year distances blur the line between the known and the unknowable, lies a fundamental truth. Much of what holds existence together remains hidden from view. Dark matter, that enigmatic substance, which constitutes approximately 27% of the cosmos, operates as an invisible scaffold beneath the visible tapestry of stars and galaxies. Its gravitational embrace binds spiral arms in place, prevents galaxy clusters from tearing apart under their own motion, and seeds the cosmic web of structure we observe today. Yet, as we journey inward from the grand scale of galactic dynamics to the intimate realm of our own solar system, a tantalizing question emerges. Does this silent architect extend its influence to the outermost reaches of our celestial neighborhood? At the solar system's fringes, where sunlight fades into the void and the Oort Cloud looms like a spectral halo, could dark matter's ghostly hand stir the icy remnants of planetary formation? This inquiry bridges the macroscopic and the microscopic, linking the universe's largest structures to the delicate dance of comets that occasionally venture into the inner solar system. To explore this possibility is to peer into the shadowy corridors of physics, where unseen forces whisper secrets about the nature of reality itself. The Oort Cloud, a theoretical reservoir of trillions of icy bodies extending nearly a light year from the Sun, represents the final frontier of our solar system's gravitational dominion. It is a realm where time stretches into eons and where the Sun's pull wanes to a whisper. Here, the interplay between external gravitational influences and the sun's diminishing grasp becomes critical. If dark matter, despite its elusive nature, possesses the faintest gravitational footprint, could it nudge these distant objects from their primordial orbits? Such a hypothesis invites us to reconsider the boundaries of cosmic influence, challenging the notion that our solar system exists in isolation. The idea that an invisible, non-baryonic substance might shape the behavior of the Oort Cloud is as audacious as it is humbling, a reminder that the forces governing the cosmos remain far from fully understood. To imagine dark matter's potential role in this remote domain is to engage with a paradox. A substance that neither emits nor absorbs light, yet exerts a gravitational pull strong enough to anchor galaxies, might also exert a subtle tug on the tiniest fragments of our solar system. This duality of being both omnipresent and imperceptible lies at the heart of dark matter's enduring mystery. As we contemplate its possible interactions at the solar system's edge, we are drawn into a dialogue between the infinitesimal and the infinite, where the smallest perturbations could reverberate through the fabric of space-time. The Oort Cloud, in its quiet solitude, may thus serve not only as a repository of ancient ice, but as a cosmic detector, amplifying the faint ripples of dark matter's presence. What if the occasional comet that plunges toward the sun is not merely a relic of the past, but a messenger, carrying whispers from the unseen? Dark matter's existence is inferred not through direct observation, but through its gravitational effects, a cosmic game of hide-and-seek played across the universe. While ordinary matter, the stuff of stars, planets, and ourselves, comprises only about 5% of the cosmos, dark matter accounts for roughly 27%, with the remaining 68% attributed to dark energy, the enigmatic force driving the universe's accelerated expansion. Despite decades of research, dark matter remains one of the greatest unsolved puzzles in modern physics. It does not interact via the electromagnetic force, rendering it invisible to telescopes, and its interactions with ordinary matter are limited to gravity and possibly the weak nuclear force. This elusiveness has led scientists to propose various candidates for its composition, from hypothetical particles like WIMPs, weakly interacting massive particles, and axions to more exotic possibilities. Yet the true nature of dark matter continues to evade detection, lurking just beyond the reach of our instruments. On galactic scales, dark matter's gravitational dominance is undeniable. Galactic rotation curves, the observed velocities of stars orbiting galaxy centers, reveal that visible matter alone cannot account for the observed motion. Without the additional gravitational glue provided by dark matter, galaxies would tear themselves apart. Similarly, gravitational lensing, the bending of light around massive objects, confirms the presence of unseen mass in galaxy clusters. These phenomena have cemented dark matter's role as the backbone of cosmic structure. However, when we zoom into the scale of the solar system, the story becomes murkier. The sun's gravitational field, though immense within its immediate vicinity, diminishes rapidly with distance. At the Oort Cloud's outer edges, where the sun's influence is but a faint echo, could dark matter's feeble gravitational nudge tip the balance? Some theoretical models suggest that dark matter might form substructures within the Milky Way's dark matter halo, a diffuse, roughly spherical distribution of the substance surrounding the galaxy. These substructures, often referred to as dark matter clumps or subhalos, could theoretically interact with the Oort Cloud. If such clumps pass through the outer solar system, their gravitational influence might perturb the orbits of Oort Cloud objects, sending them spiraling inward toward the sun. However, the likelihood of such encounters depends on the density and distribution of dark matter in our local region of the galaxy. Current estimates indicate that the dark matter density near the sun is relatively low, on the order of 0.3 GeO, meaning that individual clumps would be sparse and infrequent. Conversely, many physicists argue that other factors, such as stellar and galactic tides, are far more influential in shaping the Oort Cloud's dynamics. Stellar tides arise when passing stars exert gravitational forces on the cloud, while galactic tides stem from the Milky Way's own gravitational field. These effects are well documented in the study of long-period comets, whose highly elliptical orbits suggest they originate from the Oort Cloud. Compared to these known disturbances, dark matter's influence appears negligible. The challenge lies in distinguishing between a subtle dark matter signal, the natural variability caused by other sources. Any attempt to detect dark matter's fingerprints in the Oort cloud must therefore contend with a cacophony of competing gravitational effects. Despite these challenges, the possibility of dark matter interacting with the Oort cloud remains a compelling avenue of inquiry. If such interactions exist, they would provide a novel means of probing dark matter's properties, bypassing the need for direct detection experiments that rely on rare particle collisions in underground laboratories. Instead, astronomers could analyze the statistical distribution of comet impacts or the orbital characteristics of long-period comets to infer the presence of dark matter. While this approach is fraught with uncertainty, it underscores the ingenuity required to unravel the mysteries of the unseen. In the end, whether dark matter's influence is significant or not, the mere act of seeking its traces at the solar system's edge is a testament to humanity's relentless curiosity about the cosmos. If dark matter does exert a gravitational influence on the Oort cloud, its effects would manifest as subtle perturbations in the orbits of its icy denizens. These perturbations, though minuscule, could accumulate over millions of years, gradually altering the trajectories of Oort cloud objects. Over time, such changes might result in an increased frequency of cometary visitors to the inner solar system, where their incursions become observable. Long-period comets, which take thousands to millions of years to complete an orbit, are particularly intriguing in this context. Their chaotic paths suggest that external forces, rather than internal solar system dynamics, are responsible for their activation. By analyzing the statistical patterns of these comets' origins and arrival times, astronomers might discern an underlying signal indicative of dark matter's influence. One method of detecting such a signal involves studying the spatial distribution of long-period comets. If dark matter clumps pass through the outer solar system, they could create localized regions of enhanced gravitational disturbance, akin to ripples on a pond. These disturbances might lead to an asymmetric influx of comets from specific directions, deviating from the expected random distribution caused by stellar and galactic tides. For instance, if a dark matter substructure were to traverse the Oort cloud every few million years, it could generate a periodic pattern in the arrival of comets. Detecting such a periodicity would require extensive data spanning millennia, a task that pushes the limits of observational astronomy. Yet, with the advent of large-scale sky surveys and advanced computational models, the feasibility of such analyses is growing. Another approach focuses on the energy signatures of cometary impacts. When a comet enters the inner solar system, it carries with it a record of its journey through the Oort cloud. By studying the velocity and trajectory of these comets, researchers can infer the nature of the forces that disrupted their original orbits. If dark matter were a contributing factor, its signature might appear as deviations in the expected energy distribution of incoming comets. For example, comets influenced by dark matter might exhibit slightly higher kinetic energies or follow trajectories that align with the predicted paths of dark matter substructures. While these deviations would be difficult to isolate against the backdrop of natural variability, machine learning algorithms trained on vast datasets could help identify statistically significant anomalies. The implications of such discoveries would be profound. A confirmed link between dark matter and the Oort cloud would not only validate theoretical models of dark matter distribution, but also provide a new tool for mapping the unseen architecture of the galaxy. By tracking the gravitational footprints left by dark matter clumps, astronomers could construct a three-dimensional map of the Milky Way's dark matter halo, revealing its density fluctuations and structural features. This information would complement existing techniques such as gravitational lensing and stellar kinematics, offering a more comprehensive picture of the galaxy's hidden framework. Moreover, it would demonstrate that dark matter's influence extends beyond the galactic scale, permeating the very periphery of our cosmic home. However, the absence of such a signal would not spell defeat. On the contrary, it would refine our understanding of dark matter's properties and interactions. If dark matter's influence on the Oort cloud proves undetectable, it would constrain the parameters of existing models, guiding future research toward more viable hypotheses. For instance, it might suggest that dark matter particles are even less interactive than currently assumed, or that substructures within the dark matter halo are smaller or more diffuse than predicted. Either way, the pursuit of knowledge in this realm would continue to illuminate the boundaries of our understanding, pushing the frontiers of physics ever forward. Beyond the scientific ramifications, the exploration of dark matter's potential role in the Oort Cloud invites a philosophical reflection on humanity's place in the cosmos. The idea that an invisible, intangible substance might shape the movements of celestial bodies underscores the interconnectedness of all things. It reminds us that the universe is not a collection of isolated entities, but a vast dynamic system where even the faintest forces can ripple through time and space. In this context, the Oort Cloud becomes more than a reservoir of ancient ice. It becomes a mirror, reflecting the unseen forces that bind the universe together. Each comet that dares to cross the threshold from the cloud to the inner solar system is a fleeting emissary, carrying messages from the dark, and reminding us that the cosmos is far richer and stranger than we can imagine. As we shift our gaze from the Oort Cloud's distant fringes to the immediate boundary of the sun's influence, we arrive at the Heliosphere, a colossal magnetic bubble that shields our solar system from the harsh winds of interstellar space. This invisible shield, forged by the sun's solar wind, extends billions of kilometers into the void, marking the edge of the sun's gravitational and magnetic dominion. Here, the solar wind collides with the interstellar medium, creating a complex boundary region known as the heliopause. Unlike the Oort Cloud, which is a diffuse and speculative construct, the heliosphere is a tangible, albeit invisible structure that has been directly probed by spacecraft, such as Voyager 1 and 2. These intrepid explorers have crossed the heliopause, entering the uncharted territory of interstellar space and providing invaluable insights into the sun's protective cocoon. The heliosphere's role in defining the solar system's boundary is both practical and symbolic. Practically, it acts as a barrier against cosmic rays, high-energy particles originating from outside the solar system. By deflecting a significant portion of these rays, the heliosphere reduces their impact on planetary atmospheres and surfaces, potentially influencing the habitability of worlds like Earth. Symbolically, the heliosphere represents the outer limit of the sun's reach, a demarcation line between the familiar and the unknown. Just as the Oort Cloud may bear the subtle imprint of dark matter's gravitational hand, the heliosphere embodies the sun's struggle to assert its presence in a hostile environment. Together, these two realms, the dark, distant Oort Cloud and the luminous, dynamic heliosphere, frame the solar system's place in the cosmos, each shaped by forces that lie beyond our immediate perception. As we prepare to delve deeper into the heliosphere's structure and function, we are reminded of the intricate interplay between visibility and invisibility that defines our exploration of the universe. The heliosphere, though invisible to the naked eye, is a product of the sun's radiant energy and magnetic fields. The Oort Cloud, though largely theoretical, may hold secrets about the solar system's formation and evolution. Between these two extremes lies a continuum of forces, both seen and unseen, that govern the dance of celestial bodies. The transition from contemplating dark matter's whispers at the Oort Cloud to examining the heliosphere's protective embrace invites us to consider how these forces coexist and interact. Do the gravitational perturbations caused by dark matter influence the heliosphere's stability? Does the interstellar medium, in turn, affect the Oort Cloud's dynamics? These questions underscore the unity of cosmic phenomena, where the boundaries between disciplines blur and the quest for understanding becomes a shared endeavor. With this in mind, let us turn our attention to the heliosphere, the final bastion of the sun's influence, and explore how it shapes the solar system's identity within the broader galactic landscape. By tracing the path of the solar wind and the structure of the heliosphere's layers, from the termination shock to the heliopause, we will uncover the mechanisms by which the sun asserts its presence in the interstellar void. This exploration will not only illuminate the physical processes at play, but also deepen our appreciation for the delicate balance that sustains life within our cosmic neighborhood. As we venture beyond the Oort Cloud's edge and into the heliosphere's domain, we step closer to grasping the full extent of our solar system's boundaries and the forces that define them. Beyond the familiar orbits of planets, where the icy moons of Neptune shimmer in the dim light, and the Kuiper Belt's debris whispers secrets of the solar system's youth. The sun's influence extends far beyond the visible. This invisible domain is the Heliosphere, a vast dynamic bubble of magnetized plasma and charged particles, born from the relentless solar wind, stretching billions of miles into the void. The Heliosphere acts as both a fortress and a frontier, shielding the inner solar system from the cold, indifferent expanse of interstellar space, while marking the boundary where the sun's dominion yields to the cosmos at large. At the outermost reaches of this celestial shield lies the Oort Cloud, a diffuse sphere of icy bodies thought to harbor trillions of comets, adrift in the gravitational embrace of the sun. Here, at the edge of the known, the Heliosphere's final breath meets the interstellar medium, a region where stellar winds and cosmic radiation from distant stars begin to seep into our solar neighborhood. This meeting point is not a simple line but a complex, turbulent interface, a threshold where the sun's legacy confronts the vast unknown. To understand this boundary is to grasp the delicate balance between order and chaos, between the nurturing hand of a star and the indifferent vastness of space. It is a testament to the sun's enduring power and the fragility of life within its protective embrace. The heliosphere is a product of the sun's most persistent force, the solar wind. This supersonic flow of charged particles, primarily electrons, protons, and alpha particles, erupts from the sun's corona at speeds exceeding 1,000,000 miles per hour. As these particles radiate outward, they carry with them the sun's magnetic field, weaving an invisible web across the solar system. The solar wind's journey begins near the sun, where it expands rapidly, forming a spiral pattern due to the sun's rotation, a phenomenon known as the Parker spiral. By the time it reaches the orbit of Jupiter, the solar wind has traveled so far that it begins to slow, encountering resistance from the interplanetary medium. This deceleration marks the first major transition in the heliosphere's structure, the termination shock, a turbulent boundary where the solar wind abruptly slows from supersonic to subsonic speeds. Beyond this lies the heliosheath, a vast compressed region where the solar wind continues to push outward, albeit more sluggishly, until it collides with the interstellar medium. At the very edge of the heliosphere, where the solar wind's pressure finally succumbs to the ambient density of the galaxy, lies the heliopause, the true boundary of the sun's influence. This is the point where the solar wind ceases to dominate, and the interstellar medium, composed of gas, dust, and cosmic radiation from other stars, begins to permeate the solar system. The heliopause is not a static wall, but a dynamic, undulating membrane, shaped by the motion of the sun through the galaxy and the fluctuations in the solar wind. The Voyager 1 and 2 spacecraft, launched in 1977, have become humanity's first messengers to this frontier. Voyager 1 crossed the heliopause in 2012, followed by Voyager 2 in 2018, each transmitting data from a realm where the sun's voice fades into silence. These probes revealed that the heliopause is not a sharp divide, but a transitional zone, where the solar wind and interstellar medium engage in a cosmic dance, their interactions generating waves and turbulence that ripple through the heliosphere. Yet the story does not end at the heliopause. Beyond this boundary lies the Oort Cloud, a theoretical construct named after Dutch astronomer Jan Oort, who proposed its existence in 1950 to explain the origin of long-period comets. The Oort Cloud is thought to extend from about 2,000 to 100,000 astronomical units, AU, from the Sun, forming a spherical shell that encloses the entire solar system. At such distances, the Sun's gravitational pull weakens significantly, allowing the cloud's icy inhabitants to drift in near isolation for eons. However, the Oort Cloud is not entirely detached from the heliosphere. The heliosphere's outer layers, including the heliosheath and the heliopause, create a buffer zone that modulates the influx of interstellar material into the solar system. This buffer may play a subtle but critical role in shaping the Oort Cloud's environment, influencing the trajectories of its comets and the frequency with which they venture inward toward the Sun. The interplay between the heliosphere and the interstellar medium is further complicated by the Sun's motion through the galaxy. Our solar system orbits the Milky Way at approximately 514,000 miles per hour, passing through dense molecular clouds, galactic winds, and regions of enhanced cosmic radiation. These encounters can compress or distort the heliosphere, altering its shape and size over thousands of years. For instance, when the Sun passes through a denser interstellar region, the heliosphere may shrink, allowing more cosmic rays to penetrate the inner solar system. Conversely, in regions of lower density, the heliosphere may expand, offering greater protection. These fluctuations underscore the heliosphere's dynamic nature, a living boundary that evolves in response to both internal and external forces. The relationship between the heliosphere and the Oort Cloud is one of quiet symbiosis, where the Sun's protective bubble subtly shapes the behavior of the distant Cometary reservoir. While the Oort Cloud exists far beyond the heliopause, the heliosphere's influence extends into this frigid expanse through its modulation of cosmic rays. Cosmic rays are high-energy particles accelerated by supernovae and other violent astrophysical phenomena, and they pose a significant hazard to the inner solar system. The heliosphere acts as a cosmic filter, deflecting many of these particles before they reach the planets. However, during periods of low solar activity, such as the Maunder minimum in the 17th century, the heliosphere's effectiveness diminishes, allowing more cosmic rays to infiltrate the solar system. These variations may have long-term consequences for the Oort Cloud, as increased cosmic ray exposure could alter the chemical composition of its icy bodies, or even trigger subtle changes in their orbital stability. The Oort Cloud's comets are not passive relics of the past, but dynamic objects whose trajectories are influenced by the gravitational tides of the galaxy. The Sun's movement through the Milky Way subjects the Oort Cloud to periodic gravitational disturbances from nearby stars and giant molecular clouds. These perturbations can nudge comets out of their stable orbits, sending them on long, elliptical paths toward the inner solar system. The heliosphere's role in this process is indirect yet profound. By regulating the influx of cosmic rays, the heliosphere may influence the rate at which these disturbances occur. For example, a stronger heliosphere could reduce cosmic ray penetration, potentially stabilizing the Oort Cloud's population of comets. Conversely, a weaker heliosphere might allow more cosmic rays to interact with the cloud, increasing the likelihood of orbital disruptions. While the exact mechanisms remain poorly understood, this interplay highlights the interconnectedness of the solar system and its galactic environment. Moreover, the heliosphere's evolution over millennia offers a window into the broader processes that govern stellar systems. Observations of other stars suggest that many possess similar protective bubbles, or astrospheres, created by their own stellar winds. These astrospheres likely interact with hypothetical Oort-like clouds around those stars, creating a universal template for the architecture of planetary systems. Studying the heliosphere thus provides insights into the cosmic role of stars as both creators and protectors. For instance, young stars with intense stellar winds may form robust astrospheres capable of shielding their planets from harmful radiation, fostering conditions conducive to life. In contrast, older stars with weakened stellar winds may experience a gradual erosion of their protective bubbles, exposing their planetary systems to the harsher realities of interstellar space. Such comparisons underscore the heliosphere's importance not only in our own solar system, but in the broader context of astrobiology and the search for habitable worlds. The study of the heliosphere also raises profound questions about the nature of boundaries in the universe. Is the heliopause truly the edge of the Sun's influence? Or is it merely a transitional phase in an endless continuum? The Voyager probes have detected unexpected phenomena beyond the heliopause, such as magnetic fields aligned with the interstellar medium and energetic particles originating from sources other than the Sun. These findings challenge the notion of a clear-cut division between the solar system and the galaxy, suggesting instead that the two are in constant dialogue. This perspective invites a re-evaluation of how we define the limits of a star's domain. Perhaps the heliosphere is not a rigid wall, but a porous membrane, through which the Sun and the galaxy exchange energy, matter, and information. Such an understanding deepens our appreciation of the universe's complexity and reinforces the idea that no system exists in isolation. As we contemplate the heliosphere's role in shaping the Oort Cloud and its dynamic interplay with the interstellar medium, a new imperative emerges: the need to understand how this protective barrier influences the security of life within the solar system. The Oort Cloud, though remote, is not inert. Its comets, stirred by gravitational perturbations and cosmic forces, occasionally embark on journeys toward the inner planets, carrying with them the potential for both discovery and destruction. While the heliosphere mitigates the influx of cosmic rays and interstellar material, it cannot prevent the gravitational nudges that send comets hurtling toward the Sun. Thus the question arises, how can we safeguard Earth from these ancient travelers, whose origins lie at the very edge of the Sun's influence? The answer lies not only in comprehending the heliosphere's role, but in developing strategies to detect and respond to potential threats from the Oort Cloud. This leads us to the next frontier of exploration, planetary defense, where science and vigilance converge to shield our fragile world from the remnants of the cosmos. In the vast, dark expanse of the outer solar system, beyond the reach of sunlight and human observation, lies a realm of frozen relics, the Oort Cloud. This immense spherical shell of icy bodies encircles the Sun at distances so staggering they defy comprehension. While the planets orbit the Sun in a flat disk-like plane, the Oort Cloud stretches into the void, a ghostly halo of comets and debris left over from the birth of the solar system. These objects, remnants of primordial chaos, drift in isolation for eons, their trajectories stable yet fragile. Yet the universe is not static. Gravitational tugs from passing stars, the subtle pull of the Milky Way's galactic tide, or the silent approach of an unseen interstellar traveler can perturb these distant worlds. A single disturbance is enough to send a comet hurtling toward the inner solar system, carrying with it the potential for both wonder and catastrophe. For most of human history, the threat posed by such celestial wanderers remained abstract, a distant possibility whispered in myth and speculation. But as our understanding of the cosmos has deepened, so too has our awareness of the delicate balance that sustains life on Earth. The scars left by ancient impacts, the Chicxulub crater, the Vredefort structure, the massive craters etched into the Moon and Mars, serve as stark reminders of the destructive power carried by a single speeding object from the void. While such events are rare, their consequences are apocalyptic. A comet from the Oort Cloud, if dislodged from its distant perch, could arrive at Earth with little warning, its arrival heralded only by the faintest glint of reflected sunlight in a telescope's lens. The realization that we are not immune to the capricious whims of the cosmos has sparked a quiet revolution in planetary science, the pursuit of early detection and mitigation of cosmic threat. Yet the Oort Cloud is not merely a graveyard of frozen rocks. It is a cosmic archive, a time capsule of material that predates the formation of the planets. Each comet that escapes its icy prison carries clues about the conditions of the early solar system, its composition, a window into the molecular soup from which Earth itself was born. To study these objects is to peer into the past, to unravel the chemical processes that gave rise to organic molecules, perhaps even the building blocks of life. In this dual role, as both a harbinger of destruction and a messenger from the dawn of time, the Oort Cloud occupies a unique place in the human imagination. It is a paradox of peril and promise, a reminder that the universe is both indifferent and wondrous. And as we gaze outward from our fragile blue dot, scanning the heavens for signs of approaching danger, we are confronted with a fundamental truth. Our survival depends not only on vigilance, but on our ability to harmonize with the rhythms of the cosmos. This quest for understanding has led to the development of sophisticated planetary defense systems, networks of telescopes and satellites designed to track the movements of near-Earth objects, NEOs, and predict their trajectories with increasing precision. Yet the challenge of detecting a long-period comet from the Oort Cloud is unlike any other. Unlike asteroids, which follow relatively predictable orbits within the asteroid belt or near the inner planets, these distant interlopers emerge from the unknown, their paths dictated by forces beyond our immediate grasp. Their discovery often occurs only months before a potential impact, leaving little time for response. The question then is not merely whether we can detect them, but whether we can do so in time to act. As humanity stands at the threshold of this cosmic challenge, we must confront not only the technological hurdles, but the philosophical implications of our place in the universe. Are we prepared to defend our world against the unseen? Or will we remain spectators, watching as the universe unfolds its mysteries, indifferent to the fate of a single vulnerable planet? At the heart of modern planetary defense lies a paradox. The universe is vast, yet the objects that threaten Earth are often small and elusive. Near-Earth objects, NEOs, asteroids and comets whose orbits bring them close to our planet, are the primary targets of detection campaigns. Among these, long-period comets from the Oort Cloud present the greatest challenge. Unlike short-period comets, which originate from the Kuiper Belt and return to the inner solar system on predictable cycles, long-period comets are born from the chaos of the outermost solar system. Their orbital periods can span thousands to millions of years, and their trajectories are influenced by gravitational perturbations from distant sources. When a comet is dislodged from its frozen slumber, it follows a path determined by the cumulative effects of stellar encounters, the gravitational pull of the galaxy, and the subtle, unseen forces that shape the cosmic dance of the solar system. To track these elusive travelers, astronomers rely on a network of ground and space-based observatories, each equipped with cutting-edge technology designed to pierce the veil of darkness. The Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, located on the island of Maui in Hawaii, is a prime example. With its 4-meter telescope and state-of-the-art digital camera, PAN-STARRS scans the sky nightly, capturing images of the entire visible hemisphere in multiple wavelengths. By comparing successive images, software algorithms identify moving objects against the backdrop of fixed stars, flagging potential NEOs for further analysis. Similarly, the upcoming Vera C. Rubin Observatory, currently under construction in Chile, promises to revolutionize the field. Its Legacy Survey of Space and Time, LSST, will produce an unprecedented dataset, imaging the entire southern sky every few nights with a resolution capable of detecting objects as faint as magnitude 24.5, a sensitivity sufficient to spot a kilometer-wide asteroid at a distance of tens of millions of kilometers. Together, these instruments form the backbone of the global effort to catalog and monitor potential threats. However, the detection of long-period comets remains a formidable task. Because these objects originate from the Oort Cloud, their initial discovery often occurs only after they have been perturbed into an inward trajectory. At such great distances, they appear as mere pinpricks of light, moving slowly across the sky. Their brightness is further diminished by their composition. Comets are primarily composed of ice, dust, and organic compounds, which reflect only a fraction of the sunlight they receive. Even when detected, predicting their future paths requires precise measurements of their position, velocity, and orbital parameters. This is where computational models come into play. Using Newtonian mechanics and perturbation theory, scientists simulate the gravitational interactions between the comet and all major solar system bodies, including the Sun, planets, moons, and even passing stars. These simulations generate probabilistic forecasts of the comet's trajectory, identifying potential close approaches or impact scenarios. Yet uncertainties remain, particularly for comets that experience sudden changes in their motion. Due to outgassing or fragmentation, such events can alter a comet's orbit unpredictably, complicating efforts to assess its risk. Once a potential threat is identified, the next step is to determine whether it poses an actual danger to Earth. This process involves calculating the comet's orbital elements, its semi-major axis, eccentricity, inclination, and other parameters, to establish whether its path intersects with Earth's orbit. The Torino scale, a standardized system developed by astronomers, categorizes the risk level of each object based on its size, speed, and probability of impact. Objects rated as white or green on the scale indicate minimal concern, while those labeled yellow, orange, or red signal increasing levels of urgency. For long-period comets, however, the Torino scale is less frequently applied, as their sheer rarity and uncertain trajectories make statistical assessments challenging. Instead, scientists often prioritize objects with shorter orbital periods and known impact probabilities, focusing their efforts on mitigating the most immediate threats. Despite advances in detection technology, the window for intervention remains narrow. Most long-period comets are discovered only months before their closest approach to the Sun, leaving little time to implement mitigation strategies. This limitation underscores the importance of early detection, ideally identifying a comet decades or even centuries before it reaches the inner solar system. Such foresight would allow for the deployment of deflection missions, giving humanity ample time to alter the comet's course and avoid catastrophe. However, achieving this goal requires not only technological innovation, but also a commitment to sustained investment in planetary defense infrastructure. The development of next-generation telescopes, such as the proposed Large Synoptic Survey Telescopes LSST, and space-based observatories like the Near-Earth Object Surveillance Mission, NEOSM, represents a crucial step forward. These instruments, operating in both optical and infrared wavelengths, will enhance our ability to detect dim, distant objects, significantly improving our predictive capabilities. Even with robust detection systems in place, the question of how to respond to a confirmed threat remains open. Current deflection strategies fall into two broad categories: kinetic impactors and gravitational nudges. Kinetic impactors, such as NASA's Double Asteroid Redirection Test (DART) mission, involve striking the target object with a spacecraft to alter its trajectory through momentum transfer. In contrast, gravitational nudges rely on the subtle influence of a spacecraft's mass on the object's orbit, gradually shifting its path over time. Both methods require precise targeting and extensive planning, as even minor deviations can result in unintended consequences. More radical proposals, such as the use of nuclear explosives to fragment or vaporize a threatening object, remain highly controversial due to political, ethical, and environmental concerns. As a result, most planetary defense research focuses on non-nuclear alternatives, prioritizing methods that are both technically feasible and politically acceptable. Ultimately, the success of planetary defense hinges on our ability to integrate detection, prediction, and mitigation into a cohesive strategy. This requires not only scientific expertise, but also international collaboration, as the threat of a cosmic impact is a global issue that transcends national boundaries. Organizations such as the United Nations International Asteroid Warning Network, IODWEO, and the Space Mission Planning Advisory Group, SMPAG, play a vital role in coordinating efforts among space agencies, governments, and private institutions. By fostering a culture of shared responsibility, these initiatives ensure that resources and knowledge are pooled to address the most pressing challenges. In the face of an unpredictable universe, humanity's best hope lies not in individual brilliance but in collective action, a unified front against the silent watchers of the Oort Cloud. The Oort Cloud, that vast invisible shell of icy bodies encircling the solar system, serves as a stark reminder of humanity's precarious existence in the cosmos. It is a region so remote that even our most advanced telescopes struggle to penetrate its depths, yet its inhabitants hold the potential to reshape or end life on Earth. The very existence of this cosmic reservoir underscores a fundamental truth. The universe is a dynamic, ever-changing entity, where stability is an illusion and change is the only constant. For all our technological prowess, our species remains vulnerable to forces beyond our control, forces that have shaped the history of our planet since its formation. The realization of this vulnerability compels us to confront not only the practical challenges of planetary defense, but also the deeper philosophical implications of our place in the universe. The Oort Cloud's significance extends far beyond its role as a source of potential threat. It is a relic of the solar system's infancy, a testament to the chaotic processes that gave rise to the planets, moons, and other celestial bodies we call home. Each comet that escapes its icy embrace carries with it fragments of the primordial solar nebula, preserving chemical signatures that may reveal the origins of water, organic molecules, and even the building blocks of life itself. In this sense, the Oort Cloud is not merely a danger zone, but a scientific frontier, a region that holds the key to understanding the fundamental processes that govern planetary formation and evolution. The study of these distant objects is therefore not only a matter of survival, but also a pursuit of knowledge that could redefine our understanding of the cosmos. Yet the duality of the Oort Cloud, its capacity to both destroy and enlighten, raises profound questions about humanity's relationship with the universe. On one hand, we are driven by an innate curiosity, a desire to explore and understand the mysteries that lie beyond our world. On the other, we are haunted by the awareness that our existence is contingent upon the delicate balance of natural forces, many of which operate on timescales far beyond our comprehension. This tension between curiosity and caution is emblematic of the broader human condition. We seek to master the unknown even as we recognize our own limitations. The pursuit of planetary defense then becomes not just a technical endeavor, but a symbolic act, a demonstration of our determination to safeguard the fragile oasis of life that exists on Earth. Investing in planetary defense is, in essence, an investment in the future of civilization. While the probability of a catastrophic impact from a long-period comet is exceedingly low, the potential consequences are so severe that even a minuscule risk demands our attention. The history of Earth is punctuated by such events: the Permian-Triassic extinction, the Cretaceous-Paleogene extinction, and countless others, each a sobering reminder of the power wielded by a single speeding object from the void. By developing the tools and strategies to mitigate these threats, we are not only protecting ourselves from a potential disaster, but also affirming our role as stewards of life on this planet. The effort required to detect and deflect a threatening comet is immense, but it pales in comparison to the cost of inaction. International cooperation is the cornerstone of this effort. The threat posed by cosmic impacts is a global issue, one that cannot be addressed by any single nation alone. The collaborative spirit, embodied by initiatives such as the United Nations International Asteroid Warning Network, IAWOM, and the Space Mission Planning Advisory Group, SMPAG, reflects a recognition that the survival of humanity depends on unity. These organizations facilitate the exchange of data, coordinate observation campaigns, and develop contingency plans for potential impact scenarios. They serve as a model for how nations can work together to address challenges that transcend borders, fostering a sense of shared responsibility that is essential for planetary defense. Moreover, the development of planetary defense technologies has the potential to yield benefits that extend far beyond their immediate purpose. The same innovations that enable us to track and deflect comets can also be applied to other areas of science and engineering. For instance, advancements in autonomous spacecraft navigation, materials science, and propulsion systems can contribute to the broader goals of space exploration, including the search for extraterrestrial life and the colonization of other planets. In this way, planetary defense is not an isolated endeavor, but a catalyst for progress, driving technological and scientific breakthroughs that enrich our understanding of the universe. The psychological and cultural dimensions of planetary defense are equally significant. The awareness of cosmic threats has the power to unite humanity in ways that few other issues can. It reminds us of our common destiny, of the shared fragility of our existence on a planet that is but a speck in the vast cosmic web. This perspective can inspire a renewed sense of purpose, encouraging individuals and societies to think beyond their immediate concerns and consider the long-term survival of our species. The pursuit of planetary defense is, in many ways, a reflection of our deepest aspirations to protect what we cherish, to preserve the legacy of life on Earth, and to ensure that future generations inherit a world that is safe and thriving. Looking ahead, the future of planetary defense holds the promise of transformative discoveries and technological milestones. Upcoming missions, such as the European Space Agency's Hera mission and NASA's upcoming Psyche mission, will provide valuable insights into the composition and behavior of celestial bodies, informing strategies for deflection and mitigation. Additionally, the development of artificial intelligence and machine learning algorithms is poised to revolutionize our ability to analyze astronomical data, enabling faster and more accurate predictions of potential threats. These advancements will not only enhance our capacity to respond to cosmic dangers, but also deepen our understanding of the universe, bringing us closer to the answers that have eluded us for millennia. As we stand on the cusp of this new era in planetary defense, we are reminded of the interconnectedness of all things. The comets that originate from the Oort Cloud are not isolated phenomena. They are part of a larger cosmic story, one that includes the formation of the solar system, the evolution of life on Earth, and the ongoing quest for knowledge that defines our species. In protecting ourselves from these distant hazards, we are not only safeguarding our world, but also participating in the grand narrative of the universe, a story that continues to unfold with each passing moment. If the Oort Cloud is the silent guardian of the solar system's past, then the journey of a dislodged comet is a story of transformation and uncertainty. Once perturbed from its distant perch, a comet begins a slow, inexorable descent toward the inner solar system, guided by the gravitational forces of the Sun and the planets. This journey is anything but linear. It is a chaotic ballet of celestial mechanics, where the slightest nudge can alter an object's trajectory in unpredictable ways. The comet's path is shaped by the invisible hands of the cosmos, from the gentle tug of the galactic tide to the sudden, violent encounter with a passing star. As it spirals inward, its icy nucleus warms, releasing jets of gas and dust that create the luminous coma and tail that mark its arrival in the inner solar system. Understanding the dynamics of these journeys is the next step in unraveling the mystery of cometary threats and in preparing for the challenges they pose. What forces set these objects in motion? How do their orbits evolve as they interact with the planets and the Sun? And what can their paths tell us about the structure of the solar system and the nature of the universe itself? These questions lie at the heart of the next segment, where we will trace the intricate dance of comets as they navigate the gravitational labyrinth of the inner solar system. By studying their chaotic journeys, we gain not only insight into the mechanics of planetary defense, but also a deeper appreciation for the complexity and beauty of the cosmos in which we live. Beyond the orbit of Neptune, where the Sun's warmth fades to a whisper, lies the Oort Cloud, a vast spherical shell of icy bodies adrift in the abyss of space. This frozen reservoir, stretching nearly a light year from the Sun, harbors billions of comets, relics from the solar system's earliest days. These objects, born of dust and gas in the protoplanetary disk, have been cast outward by the gravitational tugs of giant planets, exiled to the cold frontier of the cosmos. For millennia, perhaps millions of years, they drift in isolation, their surfaces encrusted with methane, ammonia, and water ice, untouched by the solar wind. Yet within this desolate expanse, a delicate balance exists. The Oort Cloud is not a static tomb, but a dynamic stage where the universe's subtle forces conspire to awaken slumbering travelers. A passing star, a ripple in the galactic tide, or the faint pull of the Milky Way's gravity can disturb these icy wanderers, setting them on a trajectory toward the heart of the solar system. The journey is perilous, a cosmic lottery where only a handful of comets survive the voyage. When one does, it becomes a fleeting beacon in the night sky, a testament to the interplay of chance, time, and the invisible threads of gravity that bind the stars. To witness a comet's passage is to glimpse a fragment of the universe's ancient memory, a reminder that even in the void, the seeds of transformation lie dormant, waiting for the right moment to bloom. The first step in a comet's journey home begins with a nudge, an imperceptible disturbance that reverberates through the Oort Cloud's fragile equilibrium. These perturbations can arise from two primary sources: the gravitational influence of passing stars, or the cyclical pull of the Milky Way's galactic tide. Stars, though separated by parsecs, are not stationary. Their orbits around the galactic center bring them into occasional proximity with our solar system. When a star passes near the outer reaches of the Oort Cloud, its gravity ripples through the region like a stone dropped into a pond, scattering icy bodies into new trajectories. Similarly, the galactic tide, the differential gravitational force exerted by the Milky Way's disk, creates a rhythmic tidal-like effect on the cloud. Over millions of years, this force can compress and stretch the cloud, dislodging comets and sending them spiraling inward. Once a comet begins its descent, it enters a phase of chaotic motion, governed by the laws of orbital mechanics. At first, its path is elongated and erratic, a highly elliptical orbit that may take thousands of years to complete. During this initial plunge, the comet remains in the outer solar system, far from the Sun's glare. However, as it approaches the realm of the giant planets, Jupiter, Saturn, Uranus, and Neptune, its fate becomes intertwined with their immense gravitational fields. These planets act as cosmic gatekeepers, their massive gravity capable of either accelerating a comet's journey or redirecting it entirely. For instance, a close encounter with Jupiter might shorten the comet's orbital period, transforming it from a long-period comet with periods exceeding 200 years into a short-period comet whose orbit is confined to the inner solar system. Conversely, A gravitational slingshot effect could hurl the comet back into the depths of the Oort Cloud, or even eject it from the solar system altogether. The survival of a comet is thus a matter of probability. Of the estimated 100 billion comets in the Oort Cloud, only a minuscule fraction ever reach the inner solar system. Most are lost to ejection or collision with planets, while others decay prematurely when solar radiation strips away their volatile ices before they can be seen. Those that endure, however, undergo a metamorphosis. As they draw closer to the sun, the ice on their surfaces sublimates, forming a glowing coma and trailing tail, a spectacle that has captivated observers for millennia. The comet's nucleus, a chaotic mixture of rock, ice, and organic compounds, becomes visible as it reflects sunlight, marking its triumphant return to the realm of warmth and light. The randomness of a comet's journey underscores the solar system's inherent fragility. Unlike the orderly orbits of planets, the paths of comets are shaped by the capriciousness of external forces. A single stellar encounter, occurring once every few 100,000 years, can send thousands of comets careening inward in a cascade known as a comet shower. Such events may have played a role in Earth's history, delivering water and organic molecules during the late heavy bombardment era. They may also pose existential risks. The Chicxulub impactor, responsible for the extinction of the dinosaurs, is hypothesized to have originated from a comet disrupted by Jupiter's gravity. In this way, comets serve as both architects and agents of destruction, their unpredictable nature a mirror of the cosmos itself. Studying comets, therefore, is not merely an exercise in astronomy, but a key to deciphering the solar system's evolution. Observatories on Earth and in space, such as the European Space Agency's Rosetta mission, have provided unprecedented insights into these icy voyages. By analyzing the composition of cometary nuclei and their isotopic signatures, scientists trace the conditions of the protosolar nebula, revealing clues about the distribution of materials in the young solar system. Furthermore, the study of cometary orbits helps astronomers model the gravitational dynamics of the outer solar system, refining theories about the existence of hypothetical planets like Planet 9, whose gravity might subtly perturb distant comets. Yet the exploration of comets extends beyond science. It invites philosophical reflection. A comet's journey is a metaphor for transience and resilience. Born in the cold, it dares to venture toward the heat, defying the odds to shine briefly before fading into obscurity. Its tail, a trail of vaporized ice, symbolizes the ephemeral beauty of existence. In the grand tapestry of the universe, comets remind us that even the most isolated entities are connected by unseen forces, their fates intertwined with the gravitational ballet of stars and planets. They challenge our perception of time, compressing eons into moments of brilliance and urging us to contemplate our own place in the cosmic hierarchy. As we ponder the odysseys of these icy travelers, we begin to see them not merely as wandering objects, but as time capsules, carrying the imprints of the solar system's infancy. Each comet is a Rosetta Stone, its composition and orbit offering glimpses into the conditions that preceded the formation of planets. In tracing their paths, we are, in essence, conducting cosmic archaeology, unearthing the geological and chemical records of a bygone epoch. The next segment will delve deeper into this discipline, exploring how the study of comets and other primordial bodies allows us to reconstruct the history of our celestial neighborhood. By decoding these ancient messengers, we unravel the story of how stardust coalesced into worlds, and how life itself may have taken root among the planets. The journey continues, but now it is not just the comet's voyage we follow, it is our own quest to understand the origins of the universe and our place within it. In the furthest reaches of the solar system, where sunlight dims to a ghostly shimmer and the icy silence stretches across trillions of miles, lies a realm so distant it defies imagination. This is the Oort Cloud, a spherical shell of frozen debris, encasing the solar system like a celestial halo. Though invisible to even the most advanced telescopes, its presence is inferred through the occasional visitor it sends hurtling inward, a comet, glowing faintly against the blackness, bearing fragments of a time when the planets were still forming. The Oort Cloud is no mere collection of ice and rock. It is a vault, a repository of primordial material untouched since the dawn of the solar system. Within its depths lie time capsules, each one a relic of the cosmic forge that birthed Earth, Mars, and the distant gas giants. To study these relics is to step into the role of cosmic archaeologists, sifting through the detritus of a younger universe to reconstruct the story of its origins. The Kuiper Belt, a closer cousin to the Oort Cloud, serves as a kind of entryway to this enigmatic frontier. While the Kuiper Belt resides at the edge of the known solar system, the Oort Cloud extends light years beyond, a vast and diffuse structure shaped by the gravitational tides of passing stars and the Milky Way itself. Together, these regions form a bridge between the inner worlds and the interstellar void, a boundary where the solar system's influence wanes and the galaxy's whispers grow louder. Yet it is the Oort Cloud that holds the greatest promise for unraveling the mysteries of our cosmic ancestry. Its inhabitants, comets, dwarf planets, and other icy bodies are remnants of the protoplanetary disk, the swirling nebula of gas and dust from which the solar system emerged over 4.5 billion years ago. These objects have spent eons in cold storage, their surfaces unaltered by the heat and dynamism of the inner planets. To analyze them is to peer backward in time, to touch the raw materials of creation before they were transformed into the familiar architecture of the solar system. Yet the Oort Cloud remains one of the most elusive frontiers in astronomy. No spacecraft has yet ventured close enough to observe it directly, and its true nature continues to be pieced together through indirect evidence and theoretical models. Comets, when they fall toward the sun, offer fleeting glimpses into this hidden world. Their trajectories, compositions, and chemical signatures serve as clues, fragments of a puzzle that spans millennia. Each comet is a messenger, a courier of ancient secrets carried on a journey that may have begun when the solar system was still a cradle of chaos. By decoding these messages, scientists hope to answer fundamental questions. How did the planets coalesce from the primordial soup? What role did the Oort Cloud play in shaping the solar system's architecture? And might similar structures orbit other stars, preserving the history of distant worlds? The quest to understand the Oort Cloud is not merely an academic pursuit, it is a voyage into the very heart of our cosmic heritage. To decipher the Oort Cloud's secrets, scientists turn to the molecular fingerprints etched into its inhabitants. Comets and Kuiper Belt objects are rich in volatile compounds, ices of water, methane, ammonia, and carbon dioxide, alongside complex organic molecules. These materials are preserved in a deep freeze, their chemical compositions largely unchanged since the solar system's inception. By analyzing the isotopic ratios within these substances, researchers can trace their origins to specific regions of the protoplanetary disk. For instance, the abundance of deuterium, a heavy isotope of hydrogen, in cometary ice suggests that these objects formed in the outer, colder reaches of the disk, where such ratios are more pronounced. This aligns with the prevailing theory that the Oort Cloud was assembled from material scattered outward by the gravitational interactions of the giant planets. One of the most striking discoveries in this field came from NASA's Stardust mission, launched in 1999 to intercept Comet Wild 2. When the probe returned samples of the comet's dust to Earth in 2006, it revealed a startling paradox. The particles contained crystalline silicate minerals, such as olivine and pyroxene, which require extremely high temperatures to form conditions typically found in the hot inner regions of the protoplanetary disk. This finding challenged the assumption that comets were purely products of the outer solar system. Instead, it suggested a dynamic, turbulent past in which materials were mixed across vast distances. Such mixing could have been driven by the migration of massive planets like Jupiter and Saturn, whose gravitational tug stirred the primordial disk like a cosmic blender. The implications are profound. The early solar system was not a static, orderly environment, but a chaotic cauldron of motion and transformation. Further evidence of this dynamism comes from the analysis of organic molecules in cometary material. Studies of the European Space Agency's Rosetta mission, which orbited Comet 67P, Churyumov-Gerasimenko from 2014 to 2016, detected amino acids, the building blocks of proteins and other complex hydrocarbons. These findings hint at the possibility that comets may have played a role in seeding life on Earth by delivering prebiotic chemicals. The presence of such molecules in the Oort cloud reinforces the idea that the processes shaping the solar system's architecture are deeply intertwined with the emergence of life. Moreover, the uniformity of certain isotopic signatures across comets and meteorites suggests that the materials used to build the planets were not confined to localized regions but were instead part of a vast interconnected network of matter. The Oort cloud, then, is not merely a graveyard of leftovers, but a living record of the solar system's formative years. Each comet is a time capsule, its chemical composition, a snapshot of conditions in the protoplanetary disk. By studying these objects, scientists can reconstruct the thermal, chemical, and mechanical history of the solar system with remarkable precision. For example, the ratio of oxygen isotopes in cometary ice can indicate whether the material originated in the disk's colder outskirts or was transported there from warmer inner regions. Similarly, the presence of noble gases trapped in cometary nuclei provides clues about the solar wind's influence during the disk's evolution. These insights are not limited to the solar system alone. They offer a framework for understanding how planetary systems form around other stars. If similar processes occur elsewhere in the galaxy, the Oort cloud-like structures surrounding those stars may hold the same kind of cosmic history, waiting to be uncovered. The implications of these discoveries ripple far beyond the confines of the solar system, challenging long-held assumptions about planetary formation and the universality of cosmic processes. Traditional models of planet formation, such as the core accretion hypothesis, depict a relatively orderly progression in which solid particles gradually coalesce into planetesimals and eventually planets. However, the evidence from the Oort cloud paints a different picture, one of turbulence and upheaval. The mixing of materials across the protoplanetary disk, as seen in the Stardust and Rosetta findings, suggests that the early solar system was a dynamic environment where gravitational interactions between growing planets and their surroundings drove widespread redistribution of matter. This challenges the notion of a static, concentric disk and instead supports a model in which planets migrate across vast distances, reshaping their orbits and scattering debris in their wake. This paradigm shift has profound consequences for our understanding of not only the solar system but also the countless exoplanetary systems now being discovered. Observations of young stellar systems, such as those studied by the Atacama Large Millimeter Submillimeter Array, ALMA, reveal gaps and rings in protoplanetary disks that may be the result of planet migration. These structures bear a striking resemblance to the distribution of material in the Oort cloud, suggesting that similar processes govern the formation of planetary systems throughout the galaxy. If so, then the Oort cloud is not unique to the Sun but may be a common feature of mature planetary systems. The question then arises, what can we learn from studying these distant analogues? By identifying the signatures of Oort cloud-like structures around other stars, perhaps through the detection of long-period comets or the infrared glow of distant debris, we may uncover universal patterns in the way planets form and evolve. Moreover, the Oort cloud's role in the delivery of organic molecules and water to the inner solar system raises intriguing questions about the origins of life. If comets and asteroids were responsible for bringing these essential ingredients to Earth, then similar processes could have occurred on other planets and moons, increasing the likelihood of life elsewhere in the universe. Recent studies of Europa and Enceladus, two icy moons of Jupiter and Saturn respectively, suggest that subsurface oceans may contain the necessary conditions for life, potentially fed by organic-rich materials delivered from the outer solar system. The Oort cloud in this context becomes a critical player in the cosmic drama of habitability. Its icy inhabitants, forged in the cold darkness beyond Neptune, may have traveled across the solar system to ignite the spark of life on Earth and possibly beyond. The exploration of the Oort cloud is thus not merely an exercise in historical reconstruction, but a window into the fundamental processes that shape the universe. As technology advances, new tools are emerging to probe this distant frontier. Proposed missions, such as the Interstellar Mapping and Acceleration Probe, IMAP, and the development of next-generation space telescopes, aim to detect and characterize the faint traces of Oort cloud objects. Additionally, sample return missions targeting comets or Kuiper Belt objects could provide unprecedented insights into their composition, offering direct evidence of the solar system's earliest days. These efforts are part of a broader trend in astronomy, the transition from passive observation to active exploration, from simply cataloging celestial phenomena to engaging with them in meaningful ways. Yet, even as we push the boundaries of our knowledge, the Oort Cloud remains a humbling reminder of the vastness of the unknown. It is a testament to the resilience of science, which seeks to illuminate the shadows of the cosmos with every new discovery. The study of this distant realm is not just about understanding the past, it is about redefining our place within the universe. By decoding the Oort Cloud's secrets, we gain not only a deeper appreciation of the solar system's history, but also a renewed sense of wonder at the intricate, interconnected web of forces that have shaped our existence. As we stand on the threshold of this cosmic endeavor, the Oort Cloud beckons as both a destination and a metaphor. It represents the edge of what we know, the frontier where the familiar dissolves into the enigmatic. Yet, it is not an end but a beginning, a reminder that the universe is vast, its stories unfinished, and its mysteries waiting to be unraveled. The study of the Oort Cloud is a microcosm of humanity's broader quest to reach beyond the limits of our understanding and find meaning in the stars. With each comet that falls from the abyss and each molecule analyzed in a laboratory, we take another step toward comprehending the grand design of the cosmos. But even as we advance, we must remember that the universe is not a puzzle to be solved, but a tapestry to be appreciated. Its threads woven with the light of distant stars and the echoes of ancient collisions. What lies ahead? The future of cosmic archaeology promises to be as transformative as the discoveries of the past. New missions, new instruments, and new theories will continue to reshape our understanding of the Oort Cloud and its role in the solar system. Perhaps one day, a spacecraft will pierce the veil of the Oort Cloud, returning with samples that reveal the full breadth of its history. Until then, we must rely on the indirect evidence, the fleeting visits of comets, and the ingenuity of scientists who dare to imagine the unimaginable. In doing so, we honor the legacy of those who came before us and lay the foundation for those who will follow. The journey into the cosmos is not a solitary one. It is a collective odyssey, a shared adventure that transcends time and space. And as we look to the infinite horizon ahead, we are reminded that the universe is not only a place to explore but a story to be told, one that begins in the Oort Cloud and stretches endlessly into the unknown. In the silent vastness of space, where sunlight dims to a whisper and the solar wind dissipates into the void, lies the Oort Cloud, a sphere of frozen relics encircling our solar system like a ghostly halo. This distant frontier, stretching trillions of kilometers from the sun, marks the outermost boundary of human exploration. Yet even here, the universe reveals itself as both a threshold and a beginning. The Oort Cloud is not an end but a portal, a place where the familiar laws of physics stretch and blur against the enigmatic forces that govern the cosmos. It is here, in this twilight zone of icy comets and uncharted mysteries, that humanity's oldest impulse, curiosity, finds its most profound expression. For millennia, our species has gazed upward, seeking answers in the shimmering expanse above. Ancient stargazers etched constellations into stone. Medieval scholars charted celestial movements with quills and astrolabes. And now, we send machines across the solar system, their cameras and sensors capturing fragments of the infinite. Yet for all our progress, the universe remains an ever-receding horizon. Each discovery peels back another layer of cosmic tapestry, only to unveil deeper questions. What lies beyond the Oort Cloud? What secrets do the stars hold in their fiery hearts? How did we come to exist in a universe so vast and indifferent? These questions, unanswered and perhaps unanswerable, define the essence of exploration, not merely as a pursuit of knowledge, but as a testament to our unyielding desire to understand. The Oort Cloud is a fitting metaphor for this endeavor, a place of extremes. It exists in a liminal state between the sun's feeble influence and the boundless interstellar dark. It is a realm where time stretches into eons, where comets slumber for millions of years before a gravitational nudge sends them spiraling toward the inner solar system. To study this region is to peer into the primordial past, to touch the remnants of the solar system's birth. And yet, it is also a window to the future, a reminder that the universe is not static but dynamic, a living entity in perpetual motion. As humanity stands at the edge of this frontier, we are confronted with a paradox. We are both infinitesimal and infinite, a fleeting moment in cosmic history, yet driven to grasp eternity itself. This duality, the tension between our smallness and our ambition, is the heartbeat of the human story. Our explorations, whether through the lens of a telescope or the mind of a theorist, are acts of defiance against ignorance. They are declarations that we will not accept the limits of the known, that we will push beyond the veil of uncertainty. The Oort Cloud, then, is not merely a destination, but a symbol. It represents the boundless potential of the human spirit, a challenge to venture further, to see deeper, and to embrace the mystery that lies ahead. Humanity's journey from primitive stargazers to interplanetary explorers is a saga of ingenuity and perseverance. Long before telescopes pierced the heavens, ancient civilizations charted the stars with the naked eye, recognizing patterns in the night sky that guided their navigation and calendars. The Greeks speculated about the nature of the cosmos. Islamic scholars preserved and expanded upon these ideas during Europe's Dark Ages, and Renaissance thinkers like Galileo turned the first crude telescopes toward the moon, revealing craters and mountains that shattered the notion of a perfect celestial sphere. Each era added a brushstroke to the cosmic canvas, but it was the advent of modern science and technology that truly began to unravel the universe's secrets. Today, our tools of exploration are as diverse as they are sophisticated. Gravitational wave detectors, such as LIGO and Virgo, have opened a new window onto the universe by sensing ripples in space-time caused by cataclysmic events like colliding black holes. These instruments allow us to hear the universe in ways previously unimaginable, detecting phenomena invisible to traditional telescopes. Meanwhile, next-generation observatories like the James Webb Space Telescope peer into the infrared spectrum, capturing light from galaxies formed mere hundreds of millions of years after the Big Bang. By analyzing these ancient signals, scientists reconstruct the early history of the cosmos, tracing the formation of stars, planets, and the intricate web of dark matter that binds the universe together. Yet, even as ground-based and space-based telescopes expand our vision, we must look outward to the very edge of our own solar system for answers to some of our most pressing questions. The proposed Interstellar probe mission, designed to travel beyond 500 astronomical units, AU, aims to directly study the Oort Cloud and the Heliosphere's outer reaches. At such distances, the probe would measure the interactions between the solar wind and interstellar medium, mapping the magnetic fields and particle flows that shape our cosmic neighborhood. This mission, if realized, would transform theoretical models into empirical data, providing unprecedented insights into the mechanisms that govern the solar system's outermost layers. Artificial intelligence has become an indispensable ally in this quest. With the sheer volume of data generated by modern observatories, AI algorithms sift through petabytes of information, identifying patterns and anomalies that might escape human eyes. Machine learning models predict the trajectories of near-Earth objects, simulate the behavior of distant galaxies, and even assist in decoding the faint whispers of gravitational waves. These computational tools are not replacements for human intuition, but extensions of it, amplifying our ability to process complexity and make connections across vast datasets. The synergy between human ingenuity and technological advancement has propelled us to the cusp of a new era in exploration. From the radio dishes of the Deep Space Network, which communicate with spacecraft billions of miles away, to the cryogenic instruments of the European Space Agency's Euclid mission, which will map dark energy's influence on cosmic expansion, our capabilities continue to evolve. Each innovation brings us closer to answering fundamental questions. Is life unique to Earth? What is the ultimate fate of the universe? How did the building blocks of chemistry emerge from the primordial chaos? These inquiries, once confined to philosophy and myth, now drive the design of spacecraft, the construction of telescopes, and the algorithms that decode the cosmos. But perhaps the most profound tool in our arsenal is imagination itself. Science fiction writers, artists and dreamers have long envisioned humanity's future among the stars, their visions inspiring generations of scientists and engineers. The line between fiction and reality blurs as concepts like warp drives and quantum communication move from speculative thought to serious research. While practical challenges remain daunting, the willingness to think beyond conventional boundaries fuels breakthroughs. The same curiosity that led ancient mariners to sail uncharted seas now propels us to send robotic emissaries into the void, each step forward a testament to the power of dreaming. To explore the universe is to explore ourselves. Every leap into the unknown reflects a deeper yearning, a desire not merely to survive but to understand, to connect, and to transcend. The act of looking outward compels us to confront our place in the grander scheme of existence. When we study the Oort Cloud, we are not just observing a distant reservoir of comets. We are tracing the origins of our own solar system, peering into the crucible from which Earth and life emerged. Each discovery, whether it be the detection of dark matter's elusive particles or the characterization of an interstellar object like Oumuamua, reshapes our perception of the cosmos and by extension our role within it. Consider dark matter, the invisible scaffolding of the universe. Accounting for approximately 85% of the matter in the cosmos, it exerts gravitational influence on galaxies and galaxy clusters, yet interacts with ordinary matter in ways we barely comprehend. Its existence challenges our understanding of physics, suggesting that the universe operates under rules we have yet to decipher. Similarly, the passage of Oumuamua, a cigar-shaped interstellar object that zipped through our solar system in 2017, reminds us that we are not alone in the galactic neighborhood. Though its origins remain a mystery, its presence underscores the dynamic exchange of material between star systems, a cosmic dialogue spanning light years. These revelations, humbling in their scope, force us to acknowledge the limits of our knowledge and the vastness of what remains undiscovered. Yet, paradoxically, the more we learn, the more we recognize the fragility of our understanding. The universe does not conform to human expectations. It defies logic, delights in complexity, and often hides its truths in plain sight. Take the accelerating expansion of the universe, driven by dark energy, a phenomenon that suggests our cosmos may end in a cold, lonely Big Freeze. Such a prospect, while sobering, invites reflection on the impermanence of all things, including our own species. In the face of such cosmic indifference, our achievements seem both monumental and trivial. A single human lifetime is but a flicker compared to the age of the universe. Yet within that brief span, we have built machines to pierce the veil of the unknown and sent messages into the void, hoping to find kinship in the stars. This duality of insignificance and significance is central to the human condition. Our explorations are not driven by arrogance, but by a profound need to belong, to seek meaning in a universe that appears indifferent to our struggles. The act of exploration becomes a bridge between the personal and the universal, a way of encoding our hopes, fears, and dreams into the fabric of the cosmos. When we launch a probe toward the Oort Cloud, we carry with it the collective memory of our species, the child who first stared at the stars in wonder, the scientist who devised equations to explain their motion, the poet who wove stories from their light. In this way, every mission, every observation, is a message to the universe and perhaps to future beings who might one day decipher it. The implications of this quest extend beyond science into the realm of philosophy. What does it mean to live in a universe governed by laws so alien to our intuition? How do we reconcile our biological limitations with our intellectual hunger for the infinite? These questions have no easy answers, yet they define the trajectory of human civilization. The Copernican revolution taught us that Earth is not the center of the cosmos. The discovery of exoplanets revealed that life-sustaining worlds may be common. Each revelation strips away another layer of anthropocentrism, compelling us to view ourselves as part of a larger whole. And yet, in doing so, we find a strange comfort. The universe, in its vastness, mirrors the complexity of human consciousness. Just as galaxies are structured hierarchies of stars and dark matter, so too are we composed of atoms forged in stellar furnaces, our very existence a product of cosmic alchemy. This interplay between the macroscopic and the microscopic deepens our appreciation for the interconnectedness of all things, the carbon in our bones, the oxygen we breathe, the iron in our blood. All were created in supernovae that exploded billions of years ago. We are quite literally made of stardust, the echoes of ancient explosions woven into the fabric of life. This realization transforms the act of exploration from a mere search for knowledge into a pilgrimage of self-discovery. When we study the Oort Cloud, we are studying the raw materials of our own origins. When we peer into the depths of space, we are gazing backward in time, witnessing the conditions that gave rise to the cosmos and ourselves. Perhaps the greatest irony of exploration is that it makes us simultaneously smaller and greater. The more we uncover, the more we realize how much remains hidden, how many questions still elude us, and yet this very uncertainty fuels our progress. It is a reminder that the universe is not a puzzle to be solved, but a story to be told, one chapter at a time. In embracing this narrative, we find purpose not in conquering the unknown, but in engaging with it, in allowing the universe to shape our understanding as much as we strive to shape ours. As our gaze drifts beyond the Oort Cloud, the cosmos unfurls like an endless tapestry, each thread a possibility, each pattern a mystery. The stars shimmer with the light of ancient suns, their radiance a silent hymn to the passage of time. Planets orbit in delicate harmony, their surfaces etched with the scars of collisions and the quiet persistence of geology. Nebulae swirl in colors unseen by human eyes, their gases ignited by the heat of newborn stars. In this vast theater of existence, humanity's journey is but a single act, a fleeting yet determined pulse in the rhythm of the universe. And yet, this pulse resonates with a power that transcends scale. The same curiosity that led early humans to carve symbols into cave walls now drives us to build instruments capable of detecting gravitational waves rippling across space-time. The same wonder that inspired poets to write of celestial spheres now fuels the calculations of physicists modeling the birth of galaxies. In every direction we turn, the universe offers both challenge and invitation, a call to deepen our connection to the cosmic dance in which we are all participants. As we stand at this crossroads of the known and the unknowable, we are reminded that exploration is not a finite endeavor. It is a continuum, an eternal spiral outward and inward, where each answer begets a dozen new questions. The Oort Cloud, with its icy sentinels and unseen forces, is merely one waypoint in this journey. Beyond it lie the interstellar void, the galactic arms of the Milky Way, and the distant galaxies whose light has traveled for billions of years to reach us. Each of these realms holds secrets waiting to be uncovered, stories waiting to be told. In the final moments of this contemplation, let the universe speak through its silence. Let the images of swirling galaxies and colliding stars fill your mind, their beauty a testament to the creative forces that shape reality. Let the hum of the cosmos, a symphony of electromagnetic waves, cosmic rays, and the faint echo of the Big Bang, remind you that we are part of something far greater than ourselves. And as the lights of Earth fade behind us and the stars grow brighter, remember this. The quest to explore the unknown is not just about discovering the universe. It is about discovering who we are and who we might become in the boundless expanse of the infinite horizon.